Ladies and gentlemen, welcome, very warm welcome to everybody to the BAA December meeting. I'm glad you all got here. I'm glad I got here. The weather out there is dreadful. So, big thank you for all your efforts to get here and get here on time, and I hope you have a really enjoyable afternoon. I'd like to just introduce myself. I'm Janice McLean, and I am now the incumbent of the presidency, dragged screaming into this role. But I am honoured. Thank you very much. I thank you for your support in electing me, and for the previous president. Where is he hiding, Mr. Arditi? Oh, he's powdering his nose. Well, you'll pass on my regards, Helen. I wanted to thank David for his 3 years as president. Not sure I'm going to stick that. Not sure I'm going to stick it much more than today. Of course. I am deeply flattered to have been asked to be the new president of the BAA, a very esteemed organisation, and I intend to keep it that way and to increase our reputation over the next years. Thank you very much. So, welcome all to you. Have we any new members? Hello, how are you? What's your name? Tell everyone. Do stand up and say hello to it. We have a very shy new member. And your name is? Pat. Everybody knows you, don't they? Thank you for coming, Pat. Much appreciated. We hope you enjoy our meetings in the future. Okay, we have quite a packed agenda this afternoon, and I know people will want to get away fairly soon. I have a couple of little announcements made today, 2 big decisions. We have 2 new directors that will be sitting around the council. We have a new computing director by the name of Thomas Morris. Thomas, congratulations. And we also have a new meetings secretary, dragged screaming into the role. And I'd like to a warm welcome and thank you to Steve Fladgate, who you met as you came in today. Thank you very much. And long may you stay on the council. You're so going to enjoy it. Anyhow, moving on. Right, so I just want to bring in now our paper secretary. Here's David. David, I was saying thank you for your past presidency, and you missed the best bit. Okay. Jeremy, are you there?
I'm here. I hope you can hear me. I'm sorry that I can't be with you today for the obvious reason about the weather. If I may just wish you all the best, Janice, for your presidency.
Oh, thank you.
I'm sure you will enjoy it thoroughly, and I look forward to working with you. At council earlier today, 3 papers were accepted for publication in the journal. The first is an investigation into quasar downsizing, and that's by John Glover and Graham Gerard. The second is Parallel Lives in British Amateur Astronomy, Patrick Moore and Richard Baum, and that's by Bill Latherbarrow and Bill Sheehan. And the third paper is the 2023 to 2024 Western Elongation of Venus by Paul Abel. Thank you.
Is it your wish that we accept these papers?
They've been accepted.
They might change their minds. Just because you're sitting in the sun up there. All right, thank you very much, Jeremy, and thank you for the work that you do.
Thank you.
Okay, now I'm going to move on very quickly to the most pleasurable part of the year, which is to make the awards to our award winners, prize winners of the year. Nominations are put forward for people. The awards are advertised on our website each year, and nominations are put forward by members of who they think should win an award. And I know there are many previous award winners here today. So as we have some people from far afield, I'm going to start at the very beginning with the Sir Patrick Moore Prize. And I thought it would be useful to have just a little reminder of Sir Patrick Moore for those who maybe haven't heard of him before. No? I think he is well known to you all. So we have two winners for this award. First of all, we have Julian Shapiro. Hello, Julian. How are you?
I'm doing well, thank you.
And how are things in New York City?
It's nice, but very cold.
Well, it's not nice here and it's very wet. It's good to see you. So, Julian has been nominated for the Sir Patrick Moore Prize by colleagues and friends Michael Brehans and Ryan Brennan, supported by Tom Doyle. The award, for those of you who aren't aware, is a prize of £500 and a year's membership of the BAA, which may be awarded to any person, group, society or school, whether member or affiliate of the BAA or not, for one of the following areas of activity set to reflect Sir Patrick's life and enthusiasms: the encouragement of public interest in astronomy, a contribution to the understanding of the history of astronomy, outstanding observational work by a member or members under 21 years of age, encouragement of participation in observational astronomy by youngsters, and the carrying out of a collaborative research project between amateurs only or involving professionals. Julian, it gives me great pleasure to hand over this award for as an accomplished astrophotographer with high technical skill. He shares this via his website and social media to the wider community. He's one of the youngest to discover a planetary nebula with your name on it, I believe, Shapiro 1.
Yes.
And which you identified. Do you want to tell us a little bit about how you identified this?
Yeah, sure. So I discovered my first planetary nebula in late 2023, and it was through a surveying effort. So taking large mosaics of an area of sky, in particular through ionized oxygen. And through that, I compared that to the existing sky surveys and was able to identify a new object that was too faint to have been previously observed. And this object was revealed to be a planetary nebula. And it has a binary star system in the center, which is a rare and interesting feature. And we estimate that it's about 4 light years in diameter and is about 20,000 light years from Earth.
Wow. Congratulations.
Say again, sorry? I didn't hear that.
We said congratulations to you. And your
Thank
award
you.
is somewhere in the postal system on its way over. We're really pleased you could join us this afternoon. Thank you so much. All the best.
Yes, thank you. It's an honor.
In your astro career.
Thank you.
Brilliant. Now, the second award of the Sir Patrick Moore Prize is being made to Miss Marion McNeil. Please come up. Or you could come up these mistakes. You almost stand here. That's lovely. So I'm trying to condense a citation of about 3 pages, made by Lynn Smith and Callum Potter. Marion is a multifaceted and dynamic presence in the world of astronomy as a radio presenter, writer of short stories, and an overall astronomy enthusiast. She founded Inverclyde Sky Watchers, where many of us were there at Greenock earlier this year, and had a wonderful recital by the choir there too. You brought together a vibrant community of local astronomers who recently hosted our spring meeting, Greenock, as I've just said, full-on outreach at local level, which is driven by Marion, and through this and her radio space quiz program. She's run two two-day telescope schools, workshops with beavers and scouts, and astro courses for Ukrainian refugees. What do you do in your spare time?
I look after my children.
I don't know how you have time to do it all. That's
Neither do I.
absolutely fantastic. And it gives me great pleasure to present you. Have I got all the right things here? Wrong one. Excuse me. Here we go. With your prize. Certificate. You can, of course. Come over to the microphone.
Thank you very much. Oh, I can't believe that I'm just over the moon, literally, for this. So oh, shaky. So good afternoon, ladies and gentlemen. I am deeply honoured to stand here today and accept the Sir Patrick Moore Award. To be recognised in Patrick Moore's name is an extraordinary privilege, as he was a lifelong champion of making astronomy accessible to everyone. When I founded Inverclyde Skywatchers Astronomy Group on the west coast of Scotland in 2015, it was with a simple goal in mind, and that was to share the awe and wonder of the cosmos with my community. I could never have imagined that this passion would lead to the accolade as meaningful as this. This award is a recognition not just of my work, but also of the collective efforts of everyone in my group. This is truly a shared achievement and a testament to what can be accomplished when like-minded people come together. Sir Patrick Moore once said, "The more we learn about the universe, the more we realise how little we actually know." The universe has so many stories to tell, and it's up to all of us to listen, to learn, and to share them. And from the bottom of my heart, I would like to sincerely thank the British Astronomical Association for this incredible honour. This has been the best Christmas present ever. And congratulations to the other awardees, and a very, very Merry Christmas to you all. Thank you very, very much.
Congratulations. Stomachs in, girls. Thank you. Well done, Marion.
Thank you very much.
Wow, what a speech. Now I have to work out how you use not a Mac. Hey, there we go. So the next presentation is the Walter Goodacre Award, Medal and Gift. And I just give you time to have a look and refresh for yourself who Walter Goodacre was, a hero of the BAA. And we have some very fine previous winners esteemed throughout the BAA. This is the most senior award that can be given. And this year, the award is going to someone known to many of you, especially those who fight with your Meteor cameras on a regular basis. This award is going to Mr. Alex Pratt. Now, the nomination has been made by Nick James. Does anyone know who he is? Dennis Basinski, and of course, John Mason. We all know all of these fine gentlemen. And it's made for Alex's contributions to many of the sections of the BAA. He has mentored many, many people, including myself, through his work. He's constantly promoting the BAA values at home and abroad. He's a lead also at his local Leeds Astronomy Society as an expert in meteor analysis, and he also established the Nematode Network. He's active in fields of asteroid and lunar occultation. He's submitted many peer-reviewed papers to the Journal of the BAA and also international scientific journals. He's currently transcribing the observations of Melvin Taylor's notebooks for the BAA Comet and Variable Star section. Have I got that all right,
Yes.
Alex?
You just didn't add, as I warned you, I'm rather croaky at the moment.
He's a bit crooked.
So I think any handover would perhaps do the elbow tap would be appropriate.
It gives me great pleasure to give you this award.
Thank you very much. Oh. I think there's hand washing there.
Well done, Alex. Well done. Did you want to say a wee word?
Well, I was going to, but if my throat doesn't survive, I've noticed on the BAA's awards page, the web team or the editor have started putting little mini bios of the award winners. So I will send a few notes through. While my voice still survives, I was really surprised when I saw the nomination, the information come through that I'd been nominated and accepted for this. I had to read it twice to make sure they got the right person. And I was thinking, well, yes, what should I say? Because there's so many people that I work with in the BAA who are still with us. But there's many, many more who, over those years who I worked with, who no longer are. When I was a schoolboy, I was in touch with Harold Hill when he was Silver Section Director, and he inspired me to move away from the little circular blobs to get realistic representations of sunspots. And it came through to Andrew Elliott with his video techniques, to occultations, eclipses, asteroids. Melvin Taylor in Leeds and Wakefield was getting people interested in visual observing. So I think between the 3 or 4 of us, we had perhaps a planisphere each. And years later, somebody could afford a copy of Atlas Coily, as we called it. And that's how we progressed from there to what we have now.
Oh, excellent.
But I will write a little mini note for the association's website.
Thank you.
And thank you very much.
And I forgot.
Good.
Thank you. Thank you. The next award is not that one. Not that one. That one. Or have I? No, I've missed out one. Stevenson comes next. So this. Stevenson? Yeah, we're all up there. So just a little introduction. I don't know how I condense that to just 2 sentences, because this was another man who did so much in his time. But I wanted people to be aware of who these people are. And this award is being presented to Dr. Richard Miles. Is Richard on?
He's on the Zoom. I've just asked him to join, so he's there waiting.
What do I have to do?
Tom, can we put Richard? I've asked Richard's videos on there. So there he is.
Yay!
Your audio's not on though, Richard.
Your audio. We cannot hear you.
Stop swearing.
Richard, we can't hear you.
Are you only good at sign language?
Anyhow, Richard, we're going to say lots of nice things to you. And you just have to listen. And we want to say, so Richard Miles, Dr. Richard Miles, is awarded the Stevenson Award, but and token to the value of £100, nominated by Nick James, Comet Section, and Helen Asher. Richard has combined his skills in observational astronomy with his professional background as a physical chemist to formulate a theory which has strong predictive power and which is testable using observations made with amateur-sized telescopes. He's shown that a number of gases can liquefy at very low temperatures and pressures and has proposed a mechanism which allows this melting under the solid frozen crust of a comet. His cryovolcanism theories have been tested both within the BAA and through the school's involvement that he's been working with. He has been published in Icarus, and his theory is being discussed at some of the highest levels. So, no mean feat. I have a medal for you. Or I have a check.
You're still not hearing me, are you?
Thank you, Richard. Okay, so now I come to the AC Merlin Medal and gift. Right, not the best picture I could get of Mr. Merlin, but a very dapper hat, if I may say so. I'm not going to read this for you, but I'll read. Jonathan, good to see you. The winner of this award is Dr. Jonathan Shanklin, and again nominated, I think he had too many rainy, cloudy nights, by Nick James and Dennis Brzezinski. And the nomination is made. He was Comet Section Director for 25 years. You should be up here, Jonathan, come on.
I was partly
I'm waiting for you to scream.
and I'm another that's got a slightly croaky voice.
Anyhow. Did you want to sit down?
No,
You're right.
I can still just about stand.
All right. We thank you for your commentary, your contribution to the advancement of cometary astronomy, which has been immense, and during the time when digital imaging took over from visual, which I think a lot of us appreciate. It's a big change. He became one of the leading sources of magnitude data for periodic comets, and his method has become the adopted standard in many sites. This is despite keeping his day-to-day job going as a meteorologist for the British Antarctic Survey. He continues in the Comet Section as a visual observations coordinator and in data analysis, producing regular journal articles reporting on the brighter comets of each year. He's a respected authority on periodic comets now and a pillar of knowledge and advice for the current director and secretary of the Comet Section. Jonathan, well done. What can I say? Congratulations.
For the magazines and everything, you have to have the picture, don't you?
You do.
Tell us when you've got enough.
Okay. Don't forget your little check.
Thank you very much. Right. I haven't actually prepared anything to say, but what I will say is that if you want to find more about Merlin, you should go to I think it's the January 2017 journal, where Richard McKim wrote an article about him. So that gives quite a bit more background about his life. Another point is that a previous recipient of this medal was Brian Marsden, and I think the Minor Planet Centre could do with him back, really,
I think you're right.
because they can't quite interpret the rules that he set in the way that he intended them. So I've greatly enjoyed my time comet observing. I really began with one that I didn't see, which was in 1969. I got out and looked for this bright comet that was totally unmissable, but I missed it. And that's because I didn't really know the sky very well, and that pushed me towards learning where the constellations were and everything. And then my first real comet was the one that everybody remembers as a dud, which was Comet Kahute. But actually it was really quite a nice comet. So well worth a look. And then going down to Antarctica to see Halley's Comet. I didn't specifically go there to see Halley's Comet. That was a bit of an influence in my arranging the trip. And being the first person to see the comet from Antarctica, which is another sort of tick. I think in the previous slide it showed that Stevenson, or was it Goodacre, had a crater on the moon named after him. Well, I don't have that luxury, but I do have a glacier in Antarctica named after me. So I think that's probably enough from me. Thank you very much to Janice and the BAA.
Well done.
And I'll continue, hopefully, producing comet analyses for a few more years yet.
The last presentation, and it will be short, but it is the Lydia Brown presentation, an award, medal and gift. And this is made to Mr. Steve Harvey, who is unable to attend today, but I think deserves very much a mention. Lydia Brown was one of these sort of unsung heroes that keeps all the admin and stuff running in the BAA, essential to any organisation. And Steve did this particularly with the computing section. And we certainly missed him after he left. And this award has been made, nominated by David Abditi and by Dominic Ford. And it's made for his long service to the computing section, his website operations, and for all the other hard work that he put in, producing the handbook, all the data that he crunched, putting up with all the arguments about what goes in, what doesn't. And I think a very well deserved award for Steve Harvey. Right, now I can relax because I don't have anything more to say other than to introduce our first guest this evening. Now, how do I get all rid of that? It's like it's not even a Mac. Right, I would really like to welcome to you all this afternoon Professor Alan Heavens, who's Professor of Astrostatistics at Imperial College London. After studying at Cambridge, he worked for many years at the University of Edinburgh before moving to London in 2012. His research interests have covered many aspects of extracting information on the universe from cosmological survey data, as well as theory, and such as the properties of random fields as well. An extreme data comprehension technique he devised for analysing the spectra of galaxies led to the formation of a medical imaging company, Blackford Analysis, which now employs over 100 people working on AI applications to healthcare. His field of research is in astro and space sciences, AI and image processing computer software. Professor, may I welcome you to the stage. Is the universe expanding too fast? You're going to tell us all the answers.
Well, thank you very much for that nice introduction. It's a great pleasure to be here to join you for your Christmas meeting, and so thank you very much for the invitation. I'm going to talk about the expansion of the universe, and starting with some historical note that there was a crisis in the expansion rate of the universe in the last century, in the 1970s and the 1980s. There was a fierce debate about how fast the universe was expanding, with powerful figures on both sides. Alan Sandage arguing that the expansion rate was 50 kilometers per second per megaparsec. I'm not going to say that every single time, so the number will always be in those units. And on the other side, Gérard de Vaucouleurs and colleagues who were arguing that it was expanding twice as fast. And they both were vehement that the errors on their measurements were about 10%, so these numbers were poles apart. This was a crisis because with de Vauqueler's number, you can work out the age of the universe, and the age of the universe, if de Vauqueler was right, would be younger than the oldest stars in the universe. So that was awkward. And it was only really resolved in the 1990s when measurements with the Hubble Space Telescope decided that they were both wrong and it was somewhere in the middle. If we fast forward to today, the numbers are much closer together, but we still have a crisis. We have two different ways, several different ways, but two main ways of measuring the expansion rate of the universe, and one of them gives 67 and the other one gives 73. These numbers are much closer together, obviously, but the errors on these numbers are claimed to be extremely small, so these numbers are still far apart. It's a crisis because if both of these numbers are correct, then there is something that we don't understand about the universe, and I'll give you some possible reasons why that might be. Let me give you a little bit of context. The expansion of the universe was established through observations of this man that I'm sure you'll recognize. Here's some of his data from between 1914 and 1917. And what you see is that most of the 25 galaxies that are shown here show velocities with respect to us, which are positive, which means that they're moving away from the Milky Way. So with a few exceptions, just 4 of them, the galaxies are moving apart. You'll recognize this person, anybody? Very good, excellent. So it's not Hubble. Vesto Slipher is the person who made the observations, and it was Hubble who came along later, using Slipher's observations to devise the Hubble law, or as it's now sometimes called the Hubble-Lemaitre law, making the observation that if you look at galaxies which are more distant, then the recession velocities are larger, and you can see the absorption lines of calcium here for a nearby. This galaxy appears large, and the reason for that is that it's close. It has a rather small shift away from its laboratory wavelengths, but the further away you go, then the further to the red these two lines move. So you can encapsulate this expansion of the universe with this very simple law that the speed of recession is proportional to the distance, and the proportionality is Hubble's constant, or the Hubble-Lemaitre constant. So this is what we're going to be looking at, and looking at the different ways that we can measure the Hubble constant and see what we conclude. Now, the expansion of the universe was a little bit awkward for Einstein because he had earlier devised his law of gravity, general relativity, and he altered it because he was trying to explain a static universe. And so he introduced the cosmological constant into his equations, and the cosmological constant has the effect of pushing things apart. And it's sometimes referred to as his biggest blunder. It's not entirely clear whether he actually said this or not. But he rather missed a trick, because if he'd taken his original equations, he could have concluded that a static universe was not possible, and it would have to be expanding or contracting, and he could have made a prediction that the universe was not static. If he'd done that, then I think you probably agree that he probably would be famous today if he'd been able to do it. We'll come back to the cosmological constant later, because it turns out it wasn't such a blunder after all. It plays an important role, we think, in the evolution of the universe today. So what does this mean? What is the picture that we have of this expanding universe? And the picture to have is basically the same pattern. This is an approximation, but the same pattern of structures that is all moving away from each other. It's like changing the zoom lens on a camera. And if you have a motion like this, then you can easily show that if you measure velocities with respect to any of the galaxies in here, then the velocities of the other galaxies will obey Hubble's law, with the more distant ones moving faster. So that's the general picture that we have of the universe. Oops, skipped one. So how do we go about trying to measure the expansion rate? So the most direct way, although it's not completely direct is to measure the velocities, which we can do rather easily by looking at the Doppler shifts of lines, and measuring the distances. And as you're aware, I'm sure, measuring the distances is not a trivial exercise. So the way that it's done is to look for some objects which are standard candles or standard rulers. Standard candles meaning that if you look at examples of the same object at different distances, they all have the same intrinsic brightness, and then you can use them to get relative distances. So if you have a 10-watt candle, for example, then if it appears to be 4 times as faint, then it would be twice as far away. So with a standard candle, then you can measure relative distances very well. But to know the absolute distances, you have to know that it's a 10-watt candle rather than a 5-watt candle. And so the question is, how do you do that? You can do the same thing with rulers. If you have something of known length, then if it appears to subtend an angle which is half as large, then it's twice as far away. So standard candles and standard rulers are extremely useful. The question is, are there any which we can use? Now, the most useful one for this purpose is the class of objects called supernova type 1As. These are thought to be binary systems where you have a white dwarf with a companion star, and if they're close enough together, then the white dwarf can accrete material from the other star, and if enough of it falls onto the white dwarf, then the white dwarf can't support itself against gravity, and it collapses, and in doing so explodes in a supernova explosion. Now, the point about the standard candle here is that the point at which it starts to explode happens when the mass is about 1.4 solar masses, something which was calculated theoretically by Chandrasekhar a long time ago. So they should all collapse when their mass is around about 1.4 solar masses, so they're all very similar objects and have very similar intrinsic luminosities. There are some corrections to that, but empirically it seems possible to adjust them according to their colors and how long they take to decay away. But they can be used as standard candles. They're pretty rare. They occur, or supernova explosions occur round about once per 100 years in a large galaxy, so they're relatively rare, but they're extremely bright. They can reach luminosities of getting on for 1 billion times the luminosity of the sun, so you can see them to great distances. You can see them to cosmological distances where Hubble's law applies. So that seems a useful thing to do, to have. The difficulty is, how do we tell how intrinsically bright a supernova type 1A is? We need another way to, if we had one that was close by, that we could measure the distance accurately through other means, then it would be fine. We would then know what the intrinsic brightness of a supernova type 1A was, and then if we know the intrinsic luminosity, then by measuring the faintness of distant ones, we could determine the distance. But it's not easy to do that, because the methods that we have for measuring distances nearby, such as parallax, the objects have to be very close, and there aren't any supernova type 1As that are very close. The last time one went off in the galaxy was 400 years ago or something. So there aren't any close by ones that we could measure. So a key element of measuring the expansion rate of the universe is to use a second type of standard candle in order to work out what the brightness of a supernova type 1A is. So I'll spend a minute or two on this because this is sort of crucial to the whole story. So let's imagine, we're here, there's a distant supernova here in a galaxy whose redshift we can measure, so we can measure the recession velocity, but we don't know its intrinsic brightness. However, if we've got a galaxy or a set of galaxies that have both supernova type 1As in them and some other standard candle, then we can, if we know that they're at the same distance, then we can use that other standard candle to work out the distance to this galaxy that has the standard candles and the supernovae in. So that's the way that it's done, and the standard candle that is used to get us to here is the Cepheid variable stars. So Cepheid variables are relatively common. You can measure them nearby. You can measure their distances through parallax. So Cepheid variables can be, the brightness of a Cepheid variable, the intrinsic brightness can be measured. So we can use the Cepheid variable to tell us how far away these galaxies are. And then if we have a supernova in this galaxy, we can then work out the distance to this one, because the relative distances of these two will be set by the brightness of the supernovae. So there's this sort of two-step process which is involved. One technical reason why we need to go out to here is that the Hubble expansion rate is an approximation. It applies to a completely uniform universe. But the universe is not uniform. There are galaxies, there are clusters of galaxies that are pulling things around a bit, which mess up the Hubble expansion. So if you make measurements nearby, then there's the Hubble expansion, but there is also these extra so-called peculiar velocities as things fall into galaxies of clusters of galaxies and so on. And that messes up Hubble's law. So you have to go to large distances where these peculiar velocities are, relatively speaking, quite unimportant in comparison with the general expansion. And to get out to those distances, we need to have this two-step process. So Cepheid variable stars are, as the name suggests, variable. So here's an artist's impression of one which is pulsating with a regular period. And that regular period is related to the luminosity of the Cepheid star. And this was discovered by Henrietta Leavitt between 1908 and 1912, I think. And she was one of the computers at the Harvard Observatory, computers being employed to analyze the plates that were taken at the observatory and make measurements from them. And what she showed is that if you plot the luminosity of the Cepheids against their period, then their oscillation period, then they follow these straight lines. This is because they're variable. This is when they're at their brightest, and this is when they're at their faintest. So they're oscillating between these two, but they follow these very, very close relationships, which is called the Leavitt law. So I think I had it. Oh yes, here we go. So here's an example of the light curve of a Cepheid showing this regular period. It's not a sine wave, but it's regular. And a modern version of Leavitt's graph is shown here, where the luminosity and the period are very closely related. So if you measure the period, then you know the luminosity of the Cepheid. So therefore you know the distance. The luminosity is calibrated by a number of methods, but parallax is one way to do it. So if you put these together, then what you find is that the Hubble constant is 73 plus or minus 1. This error has been going down over the last number of years. In the 1990s, the error was about 8, and it's been gradually decreasing as more data has come, and it's now very precise. Another thing that you can do with these supernovae is to deduce that the universe is accelerating. That's a different story, which I'm not really going to touch on very much here. That was discovered at the very last stages of the last century. Okay, so that's the sort of direct way of measuring locally the expansion of the universe. And we get this number, more or less halfway between Sandwich and de Vauquelin. However, there are other ways to do this. And one way is to exploit the light that's left over from the Big Bang that was discovered by accident by Penzias and Wilson in 1965 when they were looking for something else. But what they found using this Holmberg detector is that there was a signal that was coming from outer space that they didn't really understand, didn't quite expect it. At some point they thought this was coming from some white dielectric material, as they described it, that had been left by some pigeons inside the antenna, and they scrubbed it out, but this little faint signal was still there, so that wasn't the cause of it. And these observations, which are probably, arguably one of the most important discoveries in science, were published here in, I think this is the Astrophysical Journal. This is one of the most important papers in science. It begins right at the bottom of the page with the exciting title of A Measurement of Excess Antenna Temperature at 4,080 megacycles per second. I would be rushing to read that if that landed on my desk. They were very cautious about what this meant. They were basically presenting the results. And the people who were, in a real sense, were scooped were these authors here, Dickey, Peebles, Roll, and Wilkinson, who had been working on this theoretically and thought we should be able to detect this radiation left over from the Big Bang, and we're in the process of designing experiments to do it. And then these guys came along and by chance happened to discover it, you know, probably months before Dickey and colleagues would have discovered it. So they put at the very end of this paper, a possible explanation for this excess is given in the accompanying paper by these authors. So what they had discovered is the radiation left over from the hot Big Bang, and we now have exquisite measurements of it, most notably from the Planck satellite. And this shows the variations in temperature of the microwave background across the sky. So there is one component of variation that comes from the Doppler shift of the Earth through the universe, which superimposes a big dipole pattern. But if you subtract that off, then what you see here are quantum fluctuations in the early universe, which we think are caused by a process called inflation in the very early stages after the Big Bang. So these fluctuations, well, maybe just to say, I don't know if anybody still has a TV like this in the attic probably somewhere, but it's said that if you take one of these old televisions and you don't tune it to a station, then the automatic gain gets cranked up an enormous amount, and apparently, although I've never checked it out, about 1 in 100 of the little flecks that you get on the screen is due to a microwave background photon that's coming to the exciting the antenna. So what we see here is some fluctuations in the temperature that are on lots of different scales simultaneously. I think you can probably see there's this sort of large scale orange area and large scale blue area here, and there's also this very mottled distribution on a scale of about 1 degree. And if you analyze this statistically, then you can basically measure the amplitude of the fluctuations on different scales, and that's what is shown in this diagram here, which is called the power spectrum. So think of it as the amplitude on different scales. This peak here corresponds to the small mottled pattern that you see here. And at the left-hand end, that's the large-scale stuff that you see. Now, this is an incredible triumph, I think, for science, because this is quite a simple situation. It's this light has been doing nothing very much for 13.8 billion years. It was emitted when the universe was very simple, only about 300,000 or 400,000 years after the Big Bang. So the universe had no galaxies, no planets, nothing. It was just an almost uniform gas of light, dark matter, ordinary matter. That's a relatively simple thing to analyze theoretically. And these are oscillations in that fluid. So you can predict theoretically what the shape of this power spectrum should be. And what you see here in the red are the measurements from the Planck satellite, and in the cyan there, or the green, you see the theoretical predictions. If you choose the various ingredients of the universe appropriately. So the theoretical curve depends on a number of things: the amount of dark matter, the amount of ordinary matter, but also on the expansion rate of the universe. So there's information in here about the expansion rate. This gives us what's called the standard model of cosmology, or lambda CDM. It consists of Einstein's cosmological constant and cold dark matter, in addition to the stuff that we're familiar with on Earth. And this is the standard model that we have, which is a universe which has only about 5% of the energy budget of the universe is in ordinary stuff, electrons, protons, neutrons, and so on. About 5 times as much as that is in the form of dark matter, whose nature we don't really know. We know some of its properties, but we don't know in detail what it is. And then the rest of it is basically what it's called dark energy here, but this is essentially equivalent to Einstein's cosmological constant. One modern manifestation of a cosmological constant is to say that the vacuum has an energy density associated with it. If the vacuum has an energy density associated with it, then it acts just like Einstein's cosmological constant. And the notion of a vacuum having energy is not entirely alien. We know that quantum mechanically you can have particles popping into existence and then annihilating in a vacuum. So the idea that there is energy associated with a vacuum is not a completely crazy idea. But we don't really know what this dark energy is. It could be a vacuum energy density, or it could be a feature of gravity. So Einstein's general relativity has cosmological constant in, doesn't really say what it is, but just says, you know, that's the law of gravity. So it could be as simple as that. It's just a feature of gravity. So how can we use this to measure the Hubble constant? Well, the feature that you can focus on is this peak here, which occurs at a scale of about 1 degree. And what it is basically a sound wave. If you take a sound wave in the early universe that starts propagating at the Big Bang, initially it will travel at about the speed of light divided by the square root of 3. It will slow down a little bit, but then when the universe recombines, when the universe gets cold enough that the electrons combine with nuclei to form atoms, then the sound speed drops almost to 0. So you have a sound wave which is propagating at some fraction of the speed of light for a certain amount of time, and then suddenly it stops. So that imprints a particular scale, let's call it the sound horizon, on the universe. And that scale is the scale of the little fluctuations that you see here. Now, so basically that's what helps to determine what the Hubble constant is. The model with these ingredients can then be fast forwarded from 300,000 years after the Big Bang, which is when this light was emitted, to the present day, and knowing the law of gravity, knowing what the constituents of the universe are, you can work out how fast it would be expanding today. And if you do that calculation, then you find a number which is 67.4 with an error of a half. So that's fairly close to the 73, but the size of the error bar is very small. The size of the error bar on the 73 is also quite small. So those two numbers, although relatively close together, are sufficiently far apart that there's something must be wrong. This is the sound of the sound waves as they evolve over time. Not at this frequency. The frequency has been increased by 10 to the power of 26 so that you can hear it. They're really quite low normally. That's basically the signal that we're picking up. If you turn the sound off now because I think one of the later videos has some music on it, which I don't particularly want to project. So that's the situation. That's the crisis that we have today. We have these two ways of determining the Hubble constant, and they don't agree. So let's have a look at what could we do to reconcile these two things. So one possibility, remember I said that to get from the microwave background 300,000 years after the Big Bang to the present day, then we have to extrapolate for 13.8 billion years. So that's quite a big extrapolation. As I say, if we know what the constituents of the universe are, if it's the cosmological constant, the amount of dark matter that we can measure, and the ordinary stuff, plus Einstein's law of gravity, then we can work out the present day. So clearly something could be different if the gravity law is different, or if the dark energy is not quite a cosmological constant, but something quite similar to it, then we could change the rate at which the universe expands at late times. So one possibility is that the dark energy is not a vacuum energy density. So a vacuum energy density, if you expand the universe, then the energy density stays the same. You still have some vacuum, okay? Normally, when you expand ordinary matter, the energy density will go down. It will get diluted. But dark energy, vacuum energy, is very strange in that respect, in that the energy density stays the same. You still have a bit of vacuum. If you expand it, then your original box has still got vacuum in it. So the energy density stays the same. In order to get something which expands a bit faster at late times, then you can do that, but the vacuum energy has to be something a little bit different, and the properties of it have to be rather strange. It has to be a quantity that whose energy density increases with time. So ordinary matter, the energy density will dilute. Vacuum energy, the energy density stays the same. This stuff would have to have an energy density that increased as the universe expanded. And that's a bit problematic because you're basically creating energy out of nothing. So this is a possible solution, but it's uncomfortable. We should probably keep an open mind because we've already introduced two things, dark matter and dark energy, that we don't have experience of on Earth. So, introducing new things into the universe is not something that we're new to. But this stuff would have to be really quite weird. It would really have to be quite strange. It also doesn't really quite agree with the measurements that we make. If you look at more distant supernovae, you can make predictions for what the expansion should look like, and for more distant supernovae, then it doesn't really fit very well. So the idea of having something that starts off like the lambda CDM model, but then at a late stage suddenly goes a little bit faster, which sounds appealing, is difficult theoretically, and it's also not really supported by the observations. So what else could we do to reconcile these two measurements? So one way is to say that our standard ruler that we're basically using the size of the angular size of these little fluctuations as a standard ruler. And as I say, the physical size of these things is the size of the sound horizon. So perhaps the sound horizon length we've calculated incorrectly. So one way to do that, or one way where that might happen, is if during the early universe, within the first 300,000 years of the Big Bang, that the sound horizon was a bit smaller. And that could happen if the expansion rate of the universe was a bit faster in the early universe than we thought. So one way to think of that approximately is to say, all right, if the universe was expanding at a faster rate early on, then there isn't as much time for the sound wave to propagate. So the sound horizon is a bit shorter. And that means that the physical length that corresponds to these fluctuations is shorter. The sound horizon is shorter. Now, we measure very precisely what the angular size of that sound horizon is. We have very precise measurements from the microwave background. They're good to 1 part in 1,000 or even better, I think. So we know the angular size. So if the ruler is a bit smaller, then to keep the angular size the same, then it needs to be a bit closer. So the light from the microwave background that has been traveling to us must have come from a surface which is closer to us in order to keep that angular size the same. And it turns out that the distance to the last scattering surface, which you see here, is inversely proportional to the expansion rate. The bigger the expansion rate, the closer that surface is to us. And that would then reconcile the measurements that with the local measurements. The Hubble constant we would deduce to be higher and in principle in agreement with the 73. How this happens, there are many ways of doing this. There's about 1 paper every week that comes out with a new idea of how to increase the expansion rate of the early universe. And usually it means introducing something like an early cosmological constant or early dark energy, which we know pushes the universe apart. Or it could even be some extra species of neutrino, sterile neutrinos, because they don't seem to interact with anything else. But as I say, hundreds and hundreds of ideas for doing this. All you need to do is to increase the expansion rate of the universe. So generally speaking, it involves introducing some extra stuff in the early universe that causes it to expand, but then you've got to get rid of it. Okay, so and it's not very obvious how you would do that. It has to go away somehow through some process which is not really understood. And why it happens at this particular stage in the universe is also not obvious. So it's possible, and this is probably the favoured general explanation to reconcile those two numbers, to have some early dark energy or something else in the early universe that it increases the expansion rate. So it's the favoured explanation, but there isn't, out of those hundreds, I would say, there isn't a sort of compelling one that says, oh, that one's theoretically motivated. Okay, so let me see. So so those are the sort of exotic possibilities that would reconcile those two numbers. Another possibility is that one of the numbers is wrong, and most of the attention has gone on the local measurements, in particular on the Cepheids. And there is a fierce debate amongst people arguing whether the Cepheids are really good standard candles. So one way to approach that is to look at some alternative standard candles to get you from the local parallax measurements to the supernovae, which can then be used. So one that's become popular, particularly useful with the advent of the James Webb Space Telescope, is a standard candle which is the tip of the red giant branch. So here's the main sequence, is the red giant branch. So this is shell burning of hydrogen, and then once the helium in the middle, there's enough helium that gets dumped inside the shell. At some point that will ignite in the helium flash, and at that point it happens when the stars are at the tip of the red giant branch, and then all hell breaks loose. But the brightness of the tip of the red giant branch is pretty insensitive to things like the metallicity and the masses of the objects. So that tip of the distribution can be used as a standard candle, and it's being increasingly used, particularly with the James Webb Space Telescope. So JWST was launched on Christmas Day in 2021, and it's providing a wealth of data on this question. why is it useful? Well, it's useful because if we look at this diagram here, we have three different types of standard candle here. There are the Cepheids, and you'll notice that these are confined to the star-forming parts of the galaxy, where there's lots of stars. So they are, it's a crowded field, so it's quite a difficult area to be working in to measure the brightnesses. The TRGB stars can be out in the outer parts where it's easy to detect them. And there's a new one called the JAGB stars, which are also pulsating stars that are also increasingly being used. So JWST is going to be getting a lot of these observations over the next years, which will give you lots of other standard candles in order to see whether there's something wrong with the Cepheids or not. Now, the interesting thing about these new standard candles is that the Hubble constant that they predict lies between the microwave background values, which are here, the 67.4, and the Cepheids that have been mostly done with the Hubble Space Telescope here. So we now have a fierce debate between Adam Rees and colleagues on the one hand, using Cepheids, and Wendy Friedman and colleagues on the other, using these other techniques. And you'll see that these measurements lie somewhere between. Now, at the moment, these error bars are quite large in comparison with the Cepheids, but as I say, JWST should get more and more of these as time goes on. Not so many more Cepheids, but many more of these. And these lower values are quite consistent with the lower values that are coming from the microwave background. Okay, so let me just finish by saying what the future will be. So part of the future is JWST, but looking a bit more into the distance, we could also use a different technique entirely based on the gravitational waves which were recently discovered. So gravitational waves are a prediction of Einstein's theory of relativity, which was supported by the famous experiments of Eddington at the eclipse of 1919, where Einstein's theory was preferred over Newton's. And you see here Einstein theory triumphs, stars not where they seemed, because they were bent by the gravity, stars not where they seemed or were calculated to be, but nobody need worry. It's a reassuring message. So Einstein was very pleased with these results because they showed his consistency with his general theory of relativity. He was so pleased that he wrote a postcard to his mother. It's in German here. It says, Liebe Mutter. I'll translate it for you. Liebe Mutter, dear mother. Unfortunately, I don't speak German, so that's as much as I can give you. He was really pleased. Okay, so how can we use these? Well, what was discovered in 1916 was gravitational waves from coalescing black holes. And when black holes get close together, then they radiate away energy and coalesce. And they radiate energy in the form of gravitational waves, which get sent out, and they're simultaneously a squashing and a stretching motion on the objects that they go through. And those were detected in 2016. And this is the first detection showing the gravitational waves as a function of time from two of the LIGO detectors. So this is a black hole merger, but the interesting thing is that one of the many gravitational wave sources involves at least one neutron star. So black holes are great, but they don't emit any significant amount of light. But if you have a merger of a neutron star, then you have the possibility of getting some photons from there as well. And that allows you to identify where the merger took place. If you can see the galaxy, you can measure the redshift of the galaxy. The measurements, detailed statistical analysis of these traces will tell you what the distance of the object is, because you can work out theoretically what the brightness, if you like, in gravitational waves should be. So you have a possibility with gravitational waves, with these so-called standard sirens, to measure the Hubble constant. And it's been done with this one system that's been measured, and the value is 70 plus or minus 10. And there's no decimal point missing here, that is 10 rather than 1. So one object is not telling us very much. It's consistent, obviously, with both values. But the point is, if we collect over time many more of these neutron star binary mergers, then that error bar will just come down and down. So in due course, which may be, well, I'm not quite sure. I mean, I think probably people were more optimistic when this first one appeared. I think within about a year of the start of operations, this one with a neutron star came, but there haven't been any more, at least none published ever since. So I think people were expecting more. So it would be nice to have a large number of these in order to get the error bar down and to avoid all of the problems with the calibration of the standard candles. So let me just finish there, just to sort of summarize where we are. We have these two measurements, the direct local measurement that gives us a high value of the expansion rate of 73, and then this low value, which is inferred from our microwave background measurements and a few others which also support this. And the reconciliation, it's not obvious. It's not easy to know what's gone wrong, or whether there's a problem somewhere, or what the theoretical explanation is to reconcile these two. It could be some weird stuff, either recent change in the dark energy density, which doesn't seem to be favoured, but something happening early on in the universe could change the size of that sound horizon and reconcile the two things. Or there could be some problem with the standard candles that have traditionally been used. And the newer ones are maybe sort of hinting in that direction, but there's now this fierce debate between the people who favour the Cepheid's approach to the other standard candles. So look out, I would say, in the near future for more observations from JWST, which will shed light on this, and in the long term, standard sirens. So I'll stop there, and I just finally say Merry Christmas.
Thank you very much. Fascinating, absolutely fascinating, and especially what's coming out of James Webb now. It's going to just throw everything up in the air and start again, isn't it?
Yes,
Yeah.
amazing.
So, have you time for a few questions?
Yeah, you can try.
Any questions from the floor? Alan?
No. When we look at these baryon acoustic oscillations, which I believe on the CMB are about, 150,000 parsecs in size, I also
150
understand
megaparsecs, yes.
If we look at the cosmic web, we see slight overabundance of galaxies, about 150 million parsecs. It would be 1,000 times bigger. Right. Imprinted on the cosmic web, which we now believe is the imprint of those acoustic oscillations. Yes. Does that give any clue to the size of H0?
Yes, it absolutely does. Yes, no, you're absolutely right. 150,000 in proper units. You're absolutely correct. And then that gets expanded to 150 megaparsecs by more or less the present day. Yes, you're right. And I mentioned actually to just touch on that you do see these sound horizon fluctuations in the pattern of the galaxy distribution. So we see that at lower redshift. So the microwave background is at a redshift of about 1,000. The baryon acoustic oscillations we measure between a redshift of about 1/2 and redshift 3 now. So you have that standard ruler whose size almost doesn't change because the sound speed at the late time, the sound speed has gone down to something so close to 0 that basically it is a standard size. So you can look at the angular size of that as a function of redshift. And that one favors the microwave background value. So, and that's one of the reasons why these late time solutions don't work very well, because they don't really account for the late time observations of the sound horizon. You don't change the sound horizon if you have late time changes to the dark energy. So that is an important part, and I'm glad you mentioned it because I was going to I was going to touch on it, but I forgot on the way. So.
Thank you. Another question?
So these two measurements might say that the rate of expansion of the universe might change with the age of the universe. But isn't there also inflation theory, which is a theory that the expansion rate of the universe accelerated right at the beginning? So how does that relate to the Hubble constant?
That's right. So Hubble constant is a bit of a misnomer because actually the Hubble parameter in there does change with time as the universe expands anyway. You're right that in the early universe you had something that where you have an accelerating universe. It's not really relevant to this because it happens in the first fraction of a second after the Big Bang, we think. So there's two periods, appear to be two periods of inflation where, if you like, gravity is sort of negative, it's pushing, and that pushing is dominating. So in the very early stages of the universe, we think that inflation period sent things apart at a very fast rate. And in that process can also generate the fluctuations that we see. So that's partly why we think that inflation happened. But then after that, then this late stage of acceleration, which has really only been dominant for the last few billion years, that is driven by the dark energy, which is, we think, something completely different from the process that started at the Big Bang. It has some similar characteristics of vacuum energy, but at very different energy scales. So it's a different process, we think. Yeah.
Okay, one last question because we're keeping
What
people
is
from
the
their tea.
universe expanding into?
Very good question.
I didn't dare ask that.
Not necessarily into anything at all. So one way to think of it is so the measurements that we have at the moment suggest that the universe is infinite. Now, that may be an approximation to the truth, but you can certainly think of a thought experiment where you have a sheet of paper, and if you make the sheet of paper infinite, so make it squared paper, and let the sheet of paper expand, so the squares on the paper get larger and larger, and the whole thing is just getting further and further apart. Any square is getting further and further apart, but it's not expanding into anything because it's infinite. So it's you can certainly think of situations, and our simplified, what are probably simplified models of the universe are like that. They would be infinite, so they're just expanding into itself. Now, whether that's an approximation to really what happened in the early universe, we don't know. I think what we do see is that we can only see a certain volume in the universe because of the light travel time, because the Big Bang happened at a particular time. We can only see something like the distance that light can travel since the Big Bang. So there's bits of the universe that we haven't seen yet, so we don't know what's happening everywhere. But what we have is consistent with a universe which is infinite.
Thank you. Well, I think we've learnt a lot from you today. Please don't run away. We'd like you to stay and join us for a glass of wine at the end of the evening, if you can. Be nice. Good. Thank you very much. Right, well, I think we all need to just clear our heads and start thinking again. Quick time for tea. And if everyone can please come back at 4:15, 16:50. Thank you. Thank you.
Sorry, John.
I still can take one of the other I'll get you to carry on.
takes resources extra. That one.
Yeah. Should be, just organise it by date modified, it should be most recent. No, that's not it. Can I have a look?
Is it in a folder or something?
No, it should just be on the
well done for taking on board. I do the similar job for the SHA, Society of History of Astronomy, and it's hard work. I'm trying to find speakers for our spring conference. You start off with lots of contacts, and then you use them.
That's all right. Can I just change them on here?
If the font exists.
I mean, if it doesn't matter if it doesn't. I just want to make it something that just make sure it's not running off the screen anywhere.
Yeah.
Thank you very much.
That should be a bit higher, that shouldn't it? UCL. Because it's.
That one's right.
Is it? Actually, yeah, it looked okay.
Yeah, that was. It's just the fonts that are not quite. If you don't mind me just looking through and messing about. Thank you. As long as everything's on the screen, it doesn't really matter. I wondered. That way.
When people walk away, they still
It fades, but I can still hear it. The ceiling microphones all over the place.
Alright, so basically we want
if
Kate to stay
if
near the
project well,
microphone.
they're still heard. It's people without microphones, if they walk away, you won't hear.
Merry Christmas when it comes. Look at that's you remember the conductor? Yes. Quiet. Well, this is her band. Oh, and you're on there as well. So here's a couple of CDs from them. Oh, you will. I had it in my bag and I thought I'd better give it to you because knowing my luck, I will bring it back. Oh, I'm sure I'm standing up here thinking, right, what am I giving people this underneath? Dad messaged me and said, oh my God, Fiona.
Yeah, perfect. Thank you very much.
Just hit that just to be safe.
Yep.
Right.
Thank you.
Sky Notes.
Sky Notes, PowerPoint, and a little video I'd just like to run during the tea break if we can. Just for when people come back.
Yes, we do. Not many, but some.
So,
That one?
No, it'll come up with Sky Notes
Oh, where's that guy? Oh,
whatever memory stick you manage to find.
where's it gone?
This is available. Yeah, there's
Ooh. Thomas Hardy. He was quite into astronomy, wasn't he? Yeah.
not seeing it properly.
I don't know. Try plugging it in a different hole. I never understand these USB memory stick things.
No, that's not quite.
It's not happy, is it?
There it is.
So it's Sky Notes and that video. So if you just copy those two over.
Why? Oh,
Is it so slow?
it's the copy in the video. That's the.
Well, they're both about 200 minutes. So. Need to get a new memory stick.
Let's see if the old one's probably doesn't help. RP security rules, the hard disk is encrypted and it has to encrypt it as it copies
Right,
it.
yeah.
That does slow it down a bit, doesn't it?
Help. But it's almost there. 2/3 the way through. Mm, 87, 88, 89, 90. It's done. Splendid. Thank you. Just have to go playing that video.
Not that one, is it? Not that. Where did it copy to? It's called Sky Notes.
Yeah. Well, it did, but it's gone somewhere that you can't find.
Yeah. Why did... Oh, weird. I never think...
Not going to see the drive again now. I think if it sees it as a Seagate drive, then you're good. If it doesn't, then...
The drive might be a bit... I think, what's your machine? It's a Windows machine, is it?
Yeah.
And that has less of a problem. It's, you know, the default for Macs is HDCP signal to try and stop copyright stuff.
Indeed.
And that plays up with our streamer.
Yeah.
If it comes to it, yours should be able to...
I'll just put it in, but...
Should be able to connect yours up.
Yeah.
Not seeing the drive. How old is the drive?
2 years.
If it's been used heavy, that might be a thing. Drives are SS
Yeah,
solid state, and there's
do.
there is a limit on read-write to
They do
SSDs or solid state.
But they copied it over to somewhere as well.
It's not even seeing it as a...
No.
It's really not... That's in. Struggling to see the drives.
Try a different hole.
Is there on that side an A?
No, because there's only USB-C on that side.
Well, yours a window machine, it's not the worst thing.
Yeah, okay.
Like I say, the biggest bug is when people have Macs and that, because of that anti-copyright protocol that defaults on Macs. You can disable it, but it's quite a deep setting on a Mac.
I know.
No, it's not copying.
Okay.
See what...
Let me just bring my machine up and see if it... Just check it will. Alan must have done that. Try plugging it in and just check it'll work. I think so, yeah. Not yet, I'm going to get one in a sec. Yeah, that's fine, Simon. So I think the easiest thing will be to just swap over. Just check the sound's working. Is the audio on? It is. Right, okay.
Should have taken a little time delay to turn on.
I'm just going to go and get a cup of tea and then I'll come back and switch it back down.
someone just said they thought they'd seen me in Greenie, and has never been to Greenie to be honest. Yeah, well, yeah, I agree. Festival. We got to do actually. My mate was there on Christmas Day. Christmas.
I think Ron got the water today.
Oh, did he? Excellent. I don't do as much as I should. I do not organise building stuff rather than doing I was here at the June. Oh, right, no, I didn't go to that one, no. Yeah, we have.
Right, ladies and gentlemen, are we all here? Put your hand up if you're not. Thank you. Thank you for coming back on time, suitably refreshed and ready for next input. I'd like to offer a very warm welcome to Dr. Kate Pattle, excuse me, Dr. Kate Pattle, who is a Royal Society University Research Fellow and proleptic lecturer in the astrophysics group. She's a lecturer at University College London. She gained her undergraduate degree at Oxford and her PhD at the University of Central Lancashire and undertook postdoctoral work in Japan, Taiwan, and Ireland. What can I say? I mean, clearly a genius. before moving to UCL in 2021. Her research focuses on the role of magnetic fields in the star formation process, which she investigates using submillimeter wavelength telescopes, primarily the James Clerk Maxwell scope and the Atacama Large Millimeter Array scope. So a warm welcome for Kate. Working on star formation.
Thank you very much for that very kind introduction, and thank you very much for the invitation to speak here today. So I'm going to be giving us a sort of whistle-stop tour through a bit of what we know about the interstellar medium and the star formation process, and also a little bit about what we know about, or don't know about, the role that magnetic fields play in that process. So when we're talking about star-forming clouds, we're typically thinking of what, when we look in visible light, looks like nothing very much at all. This is an absolutely beautiful image that was one of the entries in this year's Astronomical Photographer of the Year competition. So if you haven't been down to the Royal Greenwich Observatory to take a look at the exhibition yet, I thoroughly encourage you to go. But I think this shows that we are looking at these dark areas where invisible or even near-infrared light we really don't see very much. These were known originally as just dark markings on the sky. This is a plate from E. Bernard's paper in, I haven't put the year on here, it was in 1919. This was one of the earliest attempts to properly catalogue these dark areas on the sky where we didn't know what was happening in them. And I was interested to realise, although I suppose I shouldn't have been surprised, that this was really deeply unsettling back in the 19th century and the early 20th century, because there were just bits of the sky where nothing was happening. I fairly recently read Two on a Tower by Thomas Hardy, which, if you haven't read it, you get a pretty good idea of what's going on in it just from this front cover image. And as you can guess, it ends, being by Thomas Hardy, it ends brilliantly for both of them. Nothing goes wrong whatsoever. They have a lovely time throughout the book. But I very much enjoyed reading it. I do think that Thomas Hardy was perhaps less interested in astronomy for its own sake and more interested in astronomy as an absolutely foolproof reason to get your hero up a mountain in the southern hemisphere at a critical juncture in the narrative in the third act. But there is a very interesting little exposition at the start that the spectacularly named Swithin St. Cleeve is giving to Lady Constantine just before she starts making decisions that she will regret for the next 300 pages. And what he's talking about is the existential horrors of astronomy. And his prime example of the kind of reason why astronomy is terrifying is the dark patches in the sky. Says something along the lines of, until a person has thought out the stars and their interspaces, he has hardly learnt that there are things much more terrible than monsters of shape, namely monsters without known shape. Such monsters are the voids and waste pieces of the sky. Look, for instance, at those pieces of darkness in the Milky Way. He goes on to name, for example, the Coal Sack Nebula, and then says, these are deep wells for the human mind to let itself down into. Now, as someone who works on the physics of star formation, I actually think not only do we have all of the nice pictures, as you will see for the rest of this talk, we also have possibly the only bit of astronomy that is guaranteed not to lead you down into a pit of existential dread, because what we're looking at here, when we look at these dark patches in the sky, are stellar nurseries. We're looking at the dark clouds of gas and dust, which are on their way to becoming new stars, new solar systems. These here, the famous pillars of creation, the stars that are forming in here will still be burning in 10 billion years' time. There are planets that haven't formed yet around these stars that could have life, perhaps something like our own. And it hasn't even got started yet. They're wonderful, wonderful things to study. They're absolutely beautiful. But also, they're really not easy to get a look at in visible light. So the image on the left here is from the Hubble Space Telescope. Please don't ask me the exact bands, because I absolutely can't remember. But looking in visible or even near-infrared light, they're still dark. And if we look again, now this is a more recent James Webb Space Telescope image a little bit further into the mid-infrared, and they're starting to become a little bit translucent. We can start to see a bit more of what's going on in there. But still, where the densest parts are, where new stars are actually forming, they're still opaque. We still can't see what's going on. So if we want to know what it is that is going on inside these star-forming nebulae, we need to go right down into the very far infrared wavelengths, or what we call the submillimeter, which, I mean, you can probably imagine from its name roughly what submillimeter wavelengths are. And then we start to see something like this. So this is a composite image of various different submillimeter wavelengths. This is the Orion B molecular cloud. Am I going to get the laser pointer? Maybe, no, I'm not. There we go. You can see here just about the famous Horsehead Nebula, which normally you would see in extinction against the background starlight. But looking at these wavelengths, we start to see it glowing. We start to see the radiation from it. And we can start to see how bright and how colourful, how beautifully structured, and how incredibly complex these star-forming clouds are. So what is it that we're actually seeing here? These clouds are primarily composed of molecular hydrogen and some helium, both of which are effectively invisible to us, which is deeply frustrating because they make up the vast majority of the mass. But we can see everything we're seeing here is radiation from dust grains. So the interstellar medium is made up of clouds of molecular hydrogen and helium mixed in with this dust. And when we say dust, it's, of course, absolutely nothing like our experience of dust in our day-to-day lives. It's more silicates, ferrous materials, carbonaceous compounds, much more like sort of sand and soot and iron filings than anything that I at least would find in my flat. In fact, it looks something like this. So this is an example of an interplanetary dust particle, actually much larger than the ones that we would find in these molecular clouds, because it's had time to grow as the solar system formed. But this was collected by a NASA stratospheric mission and observed under an electron scanning microscope. It's a few microns in size, it's complex, it's porous, but it's much, much larger than a hydrogen atom, and it radiates. And it's the radiation, the thermal radiation from these dust grains that we can observe in order to understand what's going on in these star-forming clouds of gas. So, they're radiating the submillimeter. Why is it that they're doing that? Well, just a quick recap of the electromagnetic spectrum. We are looking, when we say submillimeter, somewhere in between these two. It's not quite infrared, it's not quite microwave. Whether you consider submillimeter wavelengths to be sort of very, very long wavelength infrared or very, very short wavelength radio is really more an ecumenical matter than anything else. But the reason why we're interested in it is because these gas clouds are cold, very, very cold. They're only a few tens of degrees above absolute zero. And when you've got a relatively large object, like, for example, a few microns across dust grain, which for our purposes is fairly large, if it's in thermodynamic equilibrium with its surroundings, it emits what we call black body radiation. So, I mean, this is probably a familiar concept. Lava glows red. It's at about 1,000 degrees centigrade. A Bunsen burner in a flame is hotter than that and glows blue. If you put an infrared camera on us, we'd be glowing right now at those wavelengths. And the wavelength that you get most of your radiation at is a function of the temperature of your object. Essentially, the lower the temperature, the longer your wavelength. So the sun radiates at a central wavelength of about 0.5 micron. We're here at around about 10 microns in this room. And if you went out into interstellar molecular gas at around about 10 degrees above absolute zero, that would be radiating at around about 300 microns. So 0.3 millimeters, which I always find absolutely fascinating. Just look at it on a ruler and see the wavelengths that we're working at here. So brilliant, we'll make our telescopes. That's a nice long wavelength. We can probably make some big dishes, get a good look at that. The problem is, fine, our interstellar molecular clouds are radiating at about 10 Kelvin. So what else is radiating at about 10 radiating about 10 Kelvin, radiating at about 300 microns. What else is radiating at around about 300 microns? Water vapor. I mean, I'm very glad we've got a lot of water vapor in our atmosphere. Frankly, I think, today maybe we've got a little bit too much water vapor in our atmosphere, but this isn't something to be complaining about. We're in a very lucky position. But for the purposes of doing submillimeter astronomy, it's a little bit, doing submillimeter astronomy on the ground is a little bit like doing optical astronomy while the sky's on fire, frankly. If you get diagrams of atmospheric observation as a function of wavelength, the textbooks tend to just say the atmosphere is a wall at this point, and there's absolutely nothing you can do from the ground. That's actually not quite true, but if you want to get around the fact that we've got a lot of water vapor in our atmosphere, we have to go to somewhere extremely high up and extremely dry. So that means either the top of a mountain, that's Mauna Kea in Hawaii, which has the James Clerk Maxwell telescope at its peak, and that's the telescope that I use to do most of my own work. So the Mauna Kea has a summit height of around about 4,000 meters, which is pretty good. Even better is the Atacama Desert, 5,000 meters, and also an enormous plateau, so you can build big configurable interferometers like the ALMA array here, and that gets you above the large majority of the atmosphere, and so you do get a relatively clear view of what's going on out there at these wavelengths. However, you can do a bit better than that if you really, really want to. You can go to the top of the atmosphere. So this was, sadly it no longer exists, the Sophia Observatory. So this looks like exactly what it is. You take a Boeing 747, chop a hole in the side, put a telescope in it, fly it up to the top of the stratosphere, open it up, and get a frankly spectacular view of what's going on up there. Meanwhile, this is a military aircraft because the Federal Aviation Authority, Civil Aviation Authority took one look at it and said, no, absolutely not, what's wrong with you? It flew for a while. Sadly, NASA decided it wasn't sufficiently good value for money, which is a shame because, just ridiculous. But it did great work, some of which I'm going to show in this presentation. But of course, if you really want to get away from the atmosphere, what you can do is go above it, properly above it to space. We've had 2 submillimeter space telescopes fly, getting on for quite a while ago now, actually. 2009, we have the launch of the Planck and Herschel telescopes. We've already heard quite a lot about Planck in Alan's talk. I'm going to be talking about some of the other applications of that telescope. So Planck observed at relatively low resolution, but did take a polarimeter along, which, as you'll see later in the talk, is very useful for my purposes at least. Herschel observed at higher resolution, but just observed small parts of the sky, whereas Planck was an all-sky mission. As I understand it, cost-cutting purposes, they both went up on the same launch from French Guiana in 14th of May 2009, which is a little before I started my PhD, but I can only assume it was a very tense day for everybody in the entire far infrared and submillimeter communities. I have actually heard a fairly spectacular story about how the PI of one of the Herschel missions sent an email around the entire consortium telling everybody that the bolts that were going to separate the 2 telescopes had failed, and that ESA decided, the European Space Agency had decided that Planck was the more important mission. So Herschel was just going to have to point at whatever Planck wanted to for the next 3 years. The moral of which is, if you want to do an April Fool's joke, make sure it's actually April Fool's Day when you send the email. So, yes, this is really the only way to get an unimpeded view of the submillimeter sky is go up above the atmosphere. But space missions are expensive, they have a long lead time, and they don't come around very often. So most of what I'm going to be showing has been taken from the ground, and as you'll see, we can do a pretty good job. So this is the kind of thing that we want to look at. This is another composite image of a molecular cloud, the densest phase of the ISM. So it's complicated, there's a lot of stuff going on in there, but fundamentally what we're doing is looking at this central stage of the star formation process. So you have here sort of 2 life cycles. The life cycle of a low mass star like our sun, where it's born in one of these star-forming nebulae, spends most of its life on the main sequence, eventually becomes a red giant. When it's finished burning hydrogen into helium in its center, it becomes a planetary, throws off its outer layers, becomes a planetary nebula, and then down here, the remnants of a white dwarf, and the planetary nebula goes out into the interstellar medium, and somehow, and the textbooks tend to be a little bit fuzzy on this point, somehow the stuff that it chucks out gets reformed into star-forming nebulae, and the whole process starts again with some more heavy elements involved than it had last time round. So that's the relatively sort of calm, quiet, pedestrian way of doing things. If you're, a rock star, live fast, die young star, then you live for a much shorter amount of time, glow much brighter, become a red supergiant, explode as a supernova, and then your remnant is either a black hole or a neutron star, and still the stuff that you throw out gets regenerated somehow, mysteriously back into these star-forming nebulae. So what's actually going on inside these nebulae? What is the process? I've got to say, I don't have a very clear answer for that, because although we understand sort of in broad terms the star formation process, the actual detailed physics of how we get from A to B, how we get from a cloud of low density, turbulent, magnetized gas that's being rotated in the galactic potential and has supernovae going off on an irregular basis, to something that can collapse under gravity so far that nuclear fusion ignites in its center. It's a process that I sometimes worry we're going to wake up one day, find out it's impossible, and all vanish in a puff of logic, Douglas Adams style. But hopefully that's not going to happen. Stars do exist. And as far as we understand it, qualitatively, the process goes something like this. You start out with a cloud of molecular hydrogen gas. And what we find is universally, regardless of whether or not that cloud is sufficiently dense to actively form stars, it forms filamentary substructure. We don't see undifferentiated blobs of molecular gas floating around the interstellar medium. Wherever we look, we see substructure, and what we see is these complex networks of filaments. Sometimes those filaments are fragmenting along their own length, breaking up sort of like beads along a string into individual new star-forming cores. But if we're forming very high mass stars, what we tend to see is what we call a hub filament system, where the filaments essentially serve as accretion streams down into a dense central hub where you sort of pile up gas and massive star formation starts to happen. What we find then is we typically form clusters of young stars. It's not that common to form stars in isolation. And as far as we can tell, it's unheard of to form massive stars, so stars several times the mass of the sun by themselves. Anytime we get one extremely massive star, we get a whole collection of lower mass stars around it. What's not very clear is whether that is because it's impossible to form a high mass star by itself, whether you need to form some low mass stars and essentially one of them wins and grows and becomes high mass, or whether it's just so statistically unlikely that you make a massive star that just through sheer laws of probability, we always see some low mass ones in the same place. As yet, we don't quite know with that one. But we form these stars. Stars form in the center of envelopes of infalling gas. They form accretion disks that will eventually turn into planetary systems. And what we find is that as soon as you form a star at the center of one of these things, it starts influencing its surroundings. Partly that's because these accretion disks form because you have to shed angular momentum from these things. Angular momentum and energy gets thrown out of the system as these outflows that radiate from sort of above and below newly forming stars. That happens instantaneously. As soon as you form a star, you start getting these outflows. For massive stars, they also, well, all stars emit photons, but massive stars emit they're very hot, they emit a lot of ionizing photons. So you start forming what we call H2 regions around these stars. So this is an example here of a region where the ionizing photons from young massive stars in the center has essentially ionized the surroundings, blown away the molecular gas, and you can see a chimney all the way through this molecular cloud out to the other side, where the photons and the winds from these young massive stars have blown away their surroundings, stopped all star formation in the vicinity because they've removed all of the gas. They've piled it up elsewhere, so they might be triggering more star formation elsewhere, but in their immediate vicinity, the immediate effect of star formation is probably to suppress any more stars from forming. And of course, as I said before, the massive stars are short-lived, so they may not even look long enough to get away from the cloud that they formed in. For the most massive stars, within a few million years even, you'll get supernova explosions, which can, I mean, if we're talking about the feedback onto a cloud, this is possibly the most dramatic, well, certainly the most dramatic form. So this is my very, very brief, very cartoonish overview of the star formation process. You will notice that I've got all of this way without mentioning magnetic fields once, despite them being in my title. This is because usually if you go to any kind of astronomy talk, the joke is that if you get to the end and you haven't been paying attention and you want to ask a question, you put your hand up and say, have you considered the effects of the magnetic fields? And instantly flummox everybody. This is one of my favourite quotes from Ludwig Volcher, who said in 1967, said, "The argument in the past has been a process of elimination. You observe your phenomenon, you explain the part you can explain, and then the unexplained part is taken to show the effects of the magnetic field. It's therefore clear that the larger one's ignorance, the stronger the magnetic field." You'll notice he started this as the argument in the past, and he said this in 1967. You can decide whether in the latter end of 2024 whether we've really made any progress on this or not. Because magnetic fields are everywhere in the interstellar medium. A spiral galaxy like our Milky Way, as far as we can tell, they all have magnetic fields, and those magnetic fields run along the spiral arms. In all of these following images that I show, I'm going to be showing what we call magnetic field vectors. So these lines here indicate where we've measured, what we've measured the magnetic field direction in the plane of the sky to be. And frankly, we have to use our imagination a bit to join them up and create a coherent idea of what's going on. But for spiral galaxies, very consistently, when we look at other galaxies, we see magnetic fields that run along the spiral arms. How they actually got that way is another topic of research altogether that's definitely not come to any firm conclusions, but as far as we can tell very broadly, in early galaxies, supernovae, the first supernovae would ionize the surroundings. Where you've got ionized material, you've got moving charges, and that introduced what was called a turbulent magnetic field. And then the rotation of the galaxy has, over gigayears, converted this initial turbulent seed magnetic field into something ordered and running along the spiral arms. But there's a lot of questions, again, about how that process actually works, which I absolutely am not qualified to answer, but they are very interesting. So these magnetic fields are here, and you might ask, well, I've been talking at great length about molecular gas, molecular clouds, cold things that are not ionized particularly. So why would a molecular hydrogen cloud care in the slightest what the magnetic field is doing? The answer to that is these clouds of molecular hydrogen, they do maintain a very, very low level of ionization. Extremely low, but just high enough that you get enough collisions between ionized particles and neutral particles that they can move together. The ions move with the magnetic field, the neutrals move with the ions, and therefore the neutral gas and the magnetic fields care what each other are doing, despite the fact that they have no actual immediate influence on one another. So we know the magnetic fields are there. We know they should be influencing the dynamics of the gas. How do we measure them? How do we decide whether they're actually important or not? Well, we have three main ways, one of which I'm going to be focusing on, so I'll start with the other two. Starting with the Zeeman effect. So the Zeeman effect is the splitting of spectral lines, paramagnetic spectral lines, in the presence of a magnetic field. There's only very few molecules that this works for. H1, OHCN are the three main culprits. The reason why we like this one is because it's the only method of all the ones that I'm going to show you that actually lets us measure a magnetic field strength directly. The amount of splitting you get in a spectral line in the presence of a magnetic field is directly proportional to the strength of the field. Brilliant. Why don't we use it everywhere? Because observationally it is an absolute nightmare, to the point that I can count on the fingers of one hand, I think, the number of new measurements that have been published in the last decade. It can be done. It's incredibly observationally intensive. You need your telescope perfectly calibrated. So even though we should be using this all the time, at the moment we really don't. We use other methods that are considerably less quantitative, but considerably faster. Another method is looking at Faraday rotation. This is when you have a background source of polarized light, it passes through a molecular cloud, and you measure how much your polarization state has changed. And that gives you, if you are very, very confident that you know the density of your cloud, the length, the path length through the cloud and various other things, a way to backfigure a magnetic field strength in that cloud. For this, you need a very, very thin cloud for the light to go through, or it just gets extincted on the way past. So this works very well in sort of the peripheries of clouds when we're looking at the intergalactic medium, but it's not very much help if we want to get right down into the dense centers of these clouds where star formation is happening. So what we use instead, and this is what I'm going to be talking about for the rest of the talk, is dust polarization. So we measure the polarization state of those dust grains that I was telling you about earlier on, the ones whose emission we can measure if we observe these clouds at sub-millimeter wavelengths. This lets us observe, or at least infer, the magnetic field morphology in the plane of the sky. Not strength, just direction. It can be used to map wide areas very, very quickly. I once put on this slide observationally inexpensive, and then someone pointed out I'd got a picture from a mission that cost several billion euros and told me not to say that again. So it's quicker than the Zeeman effect by several orders of magnitude. And it lets us create maps like this. It's got many, many problems, but it does let us map what the magnetic field looks like across the entire sky. Essentially, what we're doing is taking our telescope and giving it sunglasses. So this is my favorite telescope, so obviously this is the one that gets the cool sunglasses. What we're doing is essentially taking the light that we observe from these clouds and trying to measure what the state of their polarization is. So if you have some electromagnetic waves and they don't have any particularly preferred polarization at all, and you put a polarizer in front of it, then it will block out everything but the one direction that you want to let through. And this is the principle that polarizing sunglasses use. You want to cut out the large majority of the light and just let a little bit of it through. And the angle that you choose to put your polarizer at determines what polarization angle is allowed through. So if we take one of these polarizers and rotate it in front of our telescope, then we can characterize fully the polarization state of the light. So that's what we do. But I've said all this, and I haven't actually bothered to explain why the polarization state of the emission from dust grains has any connection to the magnetic field at all. So let's just go back to our molecular cloud. This is the Ophiuchus molecular cloud. Again, I've picked a non-sub-millimeter image, so we're seeing the dust in extinction here. But if we were looking in the far infrared sub-millimeter, what we would see is a spectrum for the light that looks something like this, a black body spectrum. So those dust grains, if there were no magnetic field, they would be completely random. Like, as you saw from the electron microscope image, dust grains are not nice little spheroids, but they're also not spheres. They've got structure, they've got a long axis and they've got a short axis. And what we find, this has been known since the late 1940s, is that in the presence of a magnetic field, the dust grains align with that long axis perpendicular to the magnetic field direction. A lot of different theories were put forward for why this happens. The eventual one was only settled on maybe in the last 10 years or so, and it's not particularly direct. What we think happens is that the dust grains get hit by photons which start them spinning, and they end up, if they've got paramagnetic inclusions in them, I said ferrous materials, silicates, that sort of thing in these dust grains, they end up precessing around the magnetic field direction. So if we can measure the polarization state of the dust grains, rotate it by 90 degrees, we get a magnetic field direction in the interstellar medium. So we put our telescope between the light path, in front of the light path from one of these clouds, and we put what we call a rotating half wave plate in front of us and between our detector, our camera, and the telescope optics, so we can measure the polarization state of the light. In the specific case of JCMT, this is the pole 2 polarimeter. One of these is the polarizer, which spins, another one of which is the fixed analyzer. And here's the Scuba 2 camera. And it works. So this is the image of the magnetic field of the Milky Way that was taken by the Planck telescope. It's absolutely beautiful. I stare at this for hours. All of this had to be measured to be subtracted off in order to get at the polarization state of the cosmic microwave background, but very, very glad that that did happen because it's been of spectacular use to galactic astronomy. It shows us the structure of the magnetic field, it shows us the complexity. You can see one of the Magellanic Clouds down here. We can see the magnetic field in there as well. We can see the loops. We can see the magnetic field in the plane of the galaxy. It's everywhere. But just because there is a magnetic field and it's threading the interstellar medium on all size scales, does it actually tell us that the magnetic field is important or not? Or is it just being dragged around as the gas moves? So, very, very broadly, what we would expect magnetic fields to do is provide resistance against and also give a preferred direction to the gravitational collapse of the cloud. So if you imagine just a sphere of gas, in the absence of a magnetic field, we just expect it to collapse homologously inwards towards the center. It's a sphere, it collapses in broadly spherically. However, a magnetic field, if you've got gas in the presence of a magnetic field, it's very, very easy for it to move along the magnetic field and very, very difficult for it to move across the magnetic field lines. Like, imagine, for example, beads on a guitar string. You can rattle them up and down the strings as much as you like, or spokes on a bicycle, you know, those clacky things that you used to have on bicycle wheels. You can move them up and down the spokes as much as you like, no resistance whatsoever, but trying to get it from one string or one spoke to the next is going to be significantly harder. So what we expect is that things should collapse in along the magnetic field direction, essentially create pancake-like structures perpendicular to the magnetic field. And then eventually, when it's sufficiently dense, it will collapse inwards under gravity, dragging the magnetic field with it, creating this pinched field, what we tend to call an hourglass morphology. So that's our cartoon of what's going on. But what can we say if we do this more quantitatively? So I'm talking here only about the morphology of the magnetic field, its direction, how that direction relates to the density structure, because you're using dust polarization observations which only give us a direction and not a field strength. There is a way of trying to infer a magnetic field strength from these observations. It's absolutely horrible, and do ask me about it if you want to hear some gory details, but it's uncertain enough that I'm just going to talk about what we can tell about from the directions. So the wonderful thing about simulations is we can set our magnetic field strength. On the left here, we've got a simulation of a box with a weak magnetic field in it. And what we see in the weak field case is the magnetic field just gets dragged around. The gas moves and the magnetic field gets dragged along with it. Wherever we look, the magnetic field runs along exactly the same direction as the density structure. And here we've got the strong field case. In the strong field case, you can see it looks very different. The magnetic field, broadly speaking, is running you see these high density regions here that are running perpendicular to the local magnetic field direction. The streamlines here, you get called Van Gogh plots. The streamlines are showing the magnetic field direction, and the color scale is showing peaks in density. And the density peaks are running perpendicular to the direction of the magnetic field. So this is good for once. We've got some nice clear predictions. Weak field, the magnetic field follows the gas. Strong field, these perpendicular structures develop. This is all work that was done by Juan Soler and his collaborators. So what do we see when we look at nearby molecular clouds? So this is a Planck observation of the Taurus molecular cloud. And I mean, it's not precisely the same, but it looks a lot more like the strong field case than the weak field one. This is 10 parsecs across, so this isn't getting right down into the dense sort of hearts of the star-forming clouds. It does show us that on very large scales in the interstellar medium, we do see the magnetic field preferentially perpendicular to the density structure in these clouds, which suggests that the magnetic field has had some important role in getting them to this state. And when we observe at higher, we observe sort of deeper into the clouds with, so Planck, wonderful telescope, relatively low resolution. So, you know, this is 140 parsecs away from us, about 500 light years or so. No, sorry, slightly less than 500 light years. I can't multiply by 3 in my head under pressure, apparently. But this is the best we can do in even the most nearby clouds. If we observe with something like the JCMT, 15 meters across, we start to see in more detail what's going on here. So this is a high mass star forming region. It's a little bit further away, but you can see, again, the magnetic field very broadly is running perpendicular to this dense ridge, this dense star forming ridge has formed, and the magnetic field is on average perpendicular to it. There's a lot of complexity in what's going on in the details here. And when we zoom right into the very, very densest regions, we don't really consistently see that hourglass pinch that we expected. So although we've got fairly strong evidence that the magnetic field is important in creating clouds and getting clouds to the point of star formation, we don't yet have good evidence that it's important after that point, because at some point gravity has to win or stars would never form at all. And we think that that point is hit after you've created a cloud, after you've got it to this state, but not very long after necessarily. When you're looking at an individual stellar system that's forming, it's possible, maybe even probable, that at that point the magnetic field's just along for the ride. However, there's many more interesting things we can look at and interesting magnetic fields we can look at. This is another piece of work by the JCMT Bistro survey. I just wanted to highlight, sorry, I should have said before, this is also work from the JCMT Bistro survey that we lead at UCL, and this is work by Doris Artsemanian in Tokyo. This is the pillars of creation, which need no introduction, I think. We were able to observe the magnetic field in those pillars using the JCMT, and what we find is this is now a cloud under the kind of intense stellar feedback that creates one of those H2 regions that expands out, destroys the star-forming gas, and as it does so, it leaves behind these pillars that are gradually eroded away, become detached from the cloud, become cometary globules, and then dissipate eventually altogether. What we find is the magnetic field in, well, mostly this column, because this is the one that we detected the best, is running parallel to the length of this finger. That's not at all what the magnetic field looks like in the surrounding ionized region. It's essentially, the magnetic field runs essentially perpendicular. So we think what we have here is evidence of the magnetic field playing a role in the evolution of a cloud without necessarily being able to control what's going on. The magnetic field, this is our sort of cartoon of what's going on. A shock approaches, and as this dense structure forms, the magnetic field sort of gets dragged along behind it, essentially being reordered to be parallel to the length of the pillar. But our energetics analysis suggests that the magnetic pressure inside the pillar roughly balances the gas pressure in the surrounding H2 region. So while the magnetic field hasn't been able to prevent any of this from happening, it is playing a role in perhaps increasing the length of these pillars, the age of these pillars, keeping them connected to their parent cloud for longer, stopping them from detaching and becoming cometary globules. So we do have limited evidence from a sample size thus far of less than 5 of magnetic fields playing an important role in the evolution of clouds as stars form and as they start to ionize and destroy their surroundings. So I said in my title I was going to talk about star formation and galaxy evolution. I will just show you a gallery of some of the beautiful images of magnetic fields patterns in nearby galaxies that were taken by the Sophia telescope, the one that sadly was closed. This is all work by Enrique Lopez Rodriguez. So here you can see magnetic fields running along the arms of spiral galaxies again. And you can see, broadly speaking, this all matches the models in which we expect this to happen, but we've got a whole zoo of different behaviors in different galaxies. I'm just going to focus on one galaxy and talk about a very interesting, I think, case of how the interaction between star formation in the galaxy and the pre-existing galactic dynamo field can go. So this is the starburst galaxy M82. So it's, it's very well observed because it's absolutely beautiful, and it's got an incredible amount of star formation going on in its center. This has been triggered by an interaction with the neighbouring galaxy M81. And this is, here we've got an outflow. This outflow extends 11 kiloparsecs above and below the plane of the galaxy. And this is material that's being thrown out of the poles of the galaxy by the sheer number of supernovae that are happening in the centre. So this is work that I did with Walter Gear at the University of Galway. I went there to work with him as a postdoc, and he said, you can do any science you want, so long as it's with Scuba 2. And then I got there and said, you are going to work on other galaxies, aren't you? So I negotiated them down to nearby galaxies. And then said, well, let's point the polarimeter at it. Can we detect nearby galaxies? Well, the answer is yes, if it's as bright as this one. So we don't have a huge sample of these with the JCMT, but we do have one or two. And what we found in M82 is that what we expect in the spiral galaxy, and M82 is just about a spiral galaxy despite being classed as irregular, it has very weak spiral arms, is the magnetic field should run along those spiral arms. And that's exactly what we see in the edges of the galaxy. Out here, our signal to noise isn't great, but the field that we detect here is consistent with running along these spiral arms. What we see in the centre, though, is something completely different. There we see a magnetic field that's perpendicular to the direction of the central bar and parallel with the outflow from the plane of the galaxy. So what we think is the sheer number of supernovae going off in here, the feedback from those supernovae has completely rearranged the magnetic field of this galaxy. So that galactic dynamo effect that we expect to see in every spiral galaxy, in the presence of this much star formation, you can completely change that. You can wipe it out and instead get this behaviour here, a magnetic field in the galactic centre that connects out to that incredibly dramatic outflow, while out in the disk, where that intense star formation isn't happening, the same magnetic field that's always been there persists. This is a prediction that was made by Terry Jones back in 2000, so it's nice to see it verified. So that's just absolute whistle-stop tour of some of the things we're starting to find out with this new generation of polarimeters on the JCMT, on Sophia, and with ALMA. I didn't actually show any ALMA results, but they're absolutely beautiful. I also just wanted to mention that we're not stopping here. So I mentioned that what we want to do in these cases is go to space, and what we really want is a high resolution, high angular resolution polarimeter in space at these wavelengths, which we haven't yet had. So at the moment, we're working on pushing this concept. This is the Probe Far Infrared mission for astrophysics. NASA has said that they are going to fly either first a far infrared and then an X-ray telescope or vice versa. I'm pushing for this one because this is the resolution that we have in the off-Euclid molecular cloud that I showed a couple of times with Planck, and this is what we would be able to do with PRIMA. It would be more than an order of magnitude improvement in what we can see in these clouds. We can map the magnetic field of entire clouds in the time it currently takes us to do that, maybe that tiny little bit in the centre. And we could actually fully understand, we think, how magnetic fields transition from being important to the evolution of the interstellar medium at low column densities to just being dragged in under gravity in the highest density regions where stars form. So there's a huge amount more that we still need to learn. So please watch this space. Thank you very much.
Run away. We're not letting you off that easily. Thank you very much, Dr. Pattle. I'm sure there are lots of questions from the floor, but I just first want to say thank you for mentioning Thomas Hardy, favourite author of mine, one of the great nature poets and authors. And I always, when I go back and I read some of his books, I think how he observed and knew what was going on in the sky, there's wildlife around him, and it's a plug about light pollution, really, but how much we've lost from that he took for granted and knew how to describe.
Indeed, yeah.
So, a great author. Anyhow, enough of my observations. Let's hear from the floor. I'm sure you've many questions. John.
In one of your early slides, you showed 4 arms essentially feeding into a star-forming region and said that you then need to shed angular momentum. But if you're shedding it as a jet, don't you have to have a really, really large amount of material that gets shed to deal with the angular momentum that's come in?
It it possibly doesn't have to be a very large amount of material, so long as it's going sufficiently fast. So the actual amount of mass in a protostar system that goes out in the jets is not necessarily huge, but they are very inefficient. These cores that form into stars, probably only about 30% of their mass ends up in the star. Most of it either never makes it even into the accretion disk or gets ejected. I'm trying to remember the numbers now. It's maybe of order a few tens of percent of the mass that goes out through these jets of the stuff that goes through the accretion disk. So yes, it gets accelerated very quick. It gets accelerated a lot by the process that creates the jets. So it takes momentum out more by going fast than being massive.
And is the two-dimensional nature linked to the magnetic field? Or is it just for illustrative purposes?
So the 2D, so the one, I mean, we don't have a huge amount of certainty about what the 3D structure of these clouds is like, but we do think that we form sort of planes perpendicular to the magnetic field direction. So possibly, yes, the sort of sheet-like nature is related to the magnetic field. Within the disks that form around young stars, the two-dimensional nature of the disk is because of the angular momentum of the system, rather than anything to do with the magnetic field, we think.
Thank you. Any more questions? No? Oh, sorry, Tim. Insider knowledge here, this isn't fair.
Kate, you describe the sort of the entrainment, if that's the right word, of the neutral material flowing along the magnetic field lines, which, as I understand, is how we get the filament structure created. Do we yet actually observe the next step, as in when that transitions to the pinching or the forming of the cores, or is that still just a case of gravity wins at some stage?
It depends on who you ask, whether we've seen it or not. What some people have, so if we're in a very, very strongly magnetized case, what we would expect to happen is amber polar diffusion, so the ions and the neutrals decoupling, and the ionized material would fall in faster. Sorry, no, the neutral material would fall in faster than the ionized material. Some people say that they've seen hints of that, particularly by looking at, for example, looking at the width of filaments in unpolarized light and again in polarized light and seeing if they can measure a difference. And there's some hints of that in the observations. What we'd like to see is that hourglass field, which is sort of the smoking gun for strongly magnetized star formation. So most of the dense cores we've looked at so far, we haven't seen it. It's not clear whether that's poor sensitivity. We can't see what's going on in the extended fluffy stuff where the curved fields would be, or it's just not there. I know of one case where we might have seen it, but I'm not allowed to show the images yet. So, so jury's out. It's also not necessarily the case that there's only strong field star formation or there's only weak field star formation. There's no real reason why one cloud couldn't have a strong magnetic field and another couldn't have a weak magnetic field, and star formation proceeds differently in the two clouds. The fact that we may be seeing sort of signatures of strong field star formation occasionally, but not everywhere, does suggest that we might get different behaviours in different places. Which then begs the question of whether that actually makes any difference to the stars that form. If you get exactly the same sort of collection of stars at the end regardless of the magnetic field strength, then becomes a bit of a philosophical question whether it matters at all. But that's something we don't know yet either.
Thank you. Thanks.
Okay, well, if there's no more questions, I'll thank Dr. Pattle again and just say that was her first presentation to the BAA, and I'm sure we'll have many more. Thank you. Okay, now it's customary to have sky notes, but I'm just going to ask Nick to hang fire for a second, or you need to set up or whatever.
If I set up whilst you're...
I'll stand rattling on, thank you. That's what you're going to say. Anyhow, there's an unsung hero that for our meetings here that I've often thought is not acknowledged for all the work that he does for the BAA when we come to the IOP. So I have a little something. Is Simon allowed out of his cubby hole for a minute?
I think so. I think so.
Simon, if you'd like to come up, please.
We're talking to you, Simon.
This is Simon Clark, and Simon manages all the technology, the IT for the running of our meetings, making sure they get out to everybody else. He's been here from early morning, through our, come on up here, from our council meeting this morning, through our board of trustees. And I just want to say Merry Christmas and thank you.
Thank you.
Thank you so much for your wisdom. Okay, is it yours? So I don't think Nick should have an introduction. What will we say? This is a man who can fall off his bicycle while riding along in a straight road. I think he does something in the comments section. I don't know. Tried to explain a few things to me and failed miserably. And you are now going to do our Skynet, are you not?
I hope so.
Right.
I hope so. Thank you, Madam President, for that introduction. I'll try not to fall over during this talk, and I do have a bit of a kind of apology, I suppose, is that regulars who come to the Christmas Sky Notes expect to hear about giraffes and elephants and hippopotamuses and all sorts of things, queen-size beds, in their use of what I call non-technical units to describe sizes of things. And last Christmas, I became aware of the fact that I was being manipulated by a particular journalist who was using even more outlandish comparisons just to get into the BAA Sky Notes. So I said that I was not going to include any of these bizarre units, and I'm going to stick to that. But I'm going to start by just showing you something which I find quite entertaining. So artificial intelligence is supposed to be the great saviour of the world coming up. Our current government is planning to use it in all sorts of areas, including improving the NHS and other things. If you do Google searches these days, and I'm sure other search engines do the same thing, you get a summary from the artificial intelligence bot at the beginning of your search, telling you a kind of summary of stuff. Well, if you search for these units, this is what the Google artificial intelligence bot tells you. It says that giraffe size, sometimes used to describe asteroids, are roughly the size of a giraffe. Okay? And which we know is between 7.2, and notice it's to two significant figures, because I think they've translated it from metric. 7.2 to 16.4 feet across. But at the bottom you'll read that, however, some say that using a giraffe as a unit of measurement for asteroids is inaccurate and can lead to public underestimating the risks of dangerous asteroids. So there you go. So the Google AI bot has caught on to this thing of using these bizarre units, and I'm not going to mention them anymore. So please don't be disappointed. There aren't going to be any more mentions of bizarre units in Sky Notes. Unless I find something more interesting to talk about next time. So anyway, let's start where we normally do in Sky Notes, centre of the solar system, the sun. Something that's really quite difficult to observe at this time of year, A, because it's very low down from here, and B, because it's been blooming cloudy for a long, long time. But we are near solar maximum. Sun's been pretty active, and we've seen that in the effects that the sun has on the Earth's atmosphere. So we've seen it in having this year 2 fantastic displays of the Northern Lights. Why go to Iceland or the north of Sweden or wherever when you can actually see them from your back garden? Anyway, here's a really nice picture, white light picture by Dave Smith of the sun, showing some nice spot groups. And of course, with hydrogen alpha, you can see all sorts of other things as well. So this Anton Matthews picture in mid-November shows lots of detail there on the sun's surface. But as he commented in his submission to the BAA Observers page, you've got to be really quick at this time of year. You've got to basically be ready to go and fit into the kind of 10-15 minutes when you get a bit of clear sky during the middle of the day to try and get the sun. Peter Meadows maintains a plot of solar activity, and here we have the latest version of that, showing that the sun is near maximum at the moment. Lynn, I don't know, when is the kind of predicted maximum supposed to be? It's about now, isn't it? It's about... Oh, is it John Cook's? Sorry, I apologise to John. I got it via Peter, but I thought it was his. So we're pretty much at solar maximum, but there's been a sort of sudden real uptick this year in some very large and prominent spot groups. How long that will last for, I don't know, but they've led to some really nice displays of northern lights. And my friend Dennis Brzezinski, who lives up in the north of Scotland, just north of the Moray Firth, spends his nights these days taking pictures of the Northern Lights. And this is a lovely time lapse. This is from the October 27th display. So you can see there a really nice auroral display going on. And then here's another one that he took, I think this is, when is this? This is 10th of November. So he's really should be observing comets, but he keeps being distracted by these lights on the northern sky. And Lynn actually showed me this picture that she'd taken. I mean, this is demonstrating as well how impressive cameras are in modern mobile phones. This is taken with an iPhone. It's a picture of the Northern Lights from just the day after, the 11th of November. And I remember when we were up in Greenock and Marion put on a fantastic display of Northern Lights for us the day before the meeting. The various people managed to get some really impressive pictures of that just using handheld mobile phones. So I think, you know, my mobile phone's about 6 or 7 years old, but the one thing that would encourage me to get a new one is the quality of the cameras in them. They do seem to be really impressive. You can think of aurorae as a kind of form of light pollution, I suppose. But Robin Ledbetter, who was trying to do some spectroscopy on one of the nights when the aurora was really active, decided, well, okay, if you can't beat it, let's join it. And he actually decided to take some low-resolution spectra of the Northern Lights. So what you've got here is an animation from his all-sky camera, where that little black star is where a low-resolution spectrograph was pointing. And you can see the two lines, two big lines here are from oxygen emission at 557, I think, is the lower one, and 630 nanometers is the upper one. And he does comment that they're not exactly synchronized, so there's some very interesting physics going on there. But next time we get a bright aurora, and we've had 2 this year so far, so hopefully we'll get another one. If you have got a spectrograph, have a go at pointing it up at the sky and seeing what you can see. Certainly been amazing. I mean, the first of these saw up in Greenock was just amazing, and all of us who were up there saw a really impressive aurora. And the second one was on, I think, the 10th of October, which was really spectacular, even from where I was down in Essex. And there's certainly been something this year about having 2 really impressive aurora displays. Presumably it's destroyed the business model of all those people who want to take you to Iceland and wherever to see them, because people can tick off their bucket list because they've seen them from here. Okay, the moon. Got some nice images of the moon here. I'll mention the moon a bit later as being a bit of a nuisance, and it has been this year from the point of view of both comets and meteor showers. But the moon this year is, the full moon that's coming up on December the 15th is a particularly special full moon. It's not one of these sillily named beaver or whatever moons, but it happens to be a full moon that's occurring very close to the furthest north that the moon can get. So the planets and the sun all travel around the sky in the ecliptic. The moon's orbit is inclined to the ecliptic, and it sort of wobbles over an 18-year period, and we're approaching the point where it's at its maximum inclination, which means that the moon gets as far as it can do from the ecliptic. And this December, the moon gets about as far north as it can do. It's at a declination of something like 28 degrees north. So the sun gets to 23.5, the moon's going to get to 28. So one of the things you'll notice on December the 15th is a very bright full moon in the sky that is very, very high up as well. It's a thing called a major lunar standstill, And some people speculate that the people who built Stonehenge knew about this and did some things to align the stones there with these major lunar standstills. That's a bit speculative, but certainly this is the case. So in the winter, when we see the full moon opposite the sun, it's as high in the sky as it can possibly go. And then next summer, when it'll be low down, it'll be as low as it can possibly go. So next June, July, you'll see the full moon very, very low down on the southern horizon. So where we are at the moment, we're coming up to full, December the 15th, last quarter on December the 22nd, and then new moon right at the end of the year on December the 30th. So just a few pictures. Steve Knight submitted this really nice one of the crater Clavius, which he pointed out on the BAA Observers page was where the big monolith was found in 2001, somewhere in that crater. And Bill Leatherbarrow, this fantastic image of Sinus Iridium. Now, one thing I sort of wanted to point out is you can see here very clearly Clavius because its walls are, the sun's fairly low, so you can see the shadows in its walls. Near the top there is the crater Tycho, okay, which is a much younger crater. So Clavius is about sort of 3.5, 4 billion years old. Tycho's only just over 100 million years old. And so that's why at full moon, there's Tycho. You can see it very clearly there because it's a bright new crater. But where's Clavius? Can't see it at all. There's hardly any albedo features of Clavius at all. So those really prominent craters that you see when we're away from full, you see them in the southern highlands, just disappear completely at full moon. So again, another interesting thing, there's not a lot else you're going to be able to do on the night of December the 15th, apart from look for some Geminid meteors, which will be washed out from the moon. But have a look at the full moon and see those amazing albedo features, and particularly Tycho, the youngest large crater that we know on the moon. So starting the evening, as it's getting dark, at the moment we've got Venus, which has been gradually pulling away from the sun, but it's at a very low southern declination. So even though it's actually shortly coming up to its greatest elongation away from the sun, which will be on January the 10th, it's very low down. But many of you will have seen it. We've not had many images submitted simply because in the Northern Hemisphere it's really too low for people to be imaging. Much fainter, and again sort of disappearing down into the west, is the planet Saturn here, which has had a really good apparition this year, and it's getting gradually further north, but it's heading towards conjunction. So Saturn is essentially disappearing. It goes into conjunction with the Sun in the new year, reaches conjunction in March. So we're not going to see much more of Saturn, although there are a few things to look out for with regard to Saturn, which I'll mention in a few minutes. So if you then wait a little bit towards sort of mid-evening, two of the kind of really bright planets on view, Jupiter particularly. So Jupiter has been very bright. It's at opposition today, I think. High up in Taurus, about as high as it can get. So perfect for imaging on those lovely clear still nights that we get at this time of year. And then a little bit further to the east is Mars. So this is Mars. These are some pictures of Mars. So Mars comes to opposition next month in January. And some of the features that you can see on Mars at this time are some clouds over the volcanoes. So Mars has these big shield volcanoes. Even though it's got a very thin atmosphere, you can form clouds around them. And Richard McKim sent me some pictures, and you can see, I think, so you see those sort of white patches in the middle there. Those patches are around the central meridian, around a feature called RCA Mons. He says that if you are imaging Mars, and if you can do it with filters, these clouds are much more prominent, and that imaging with filters is actually more useful than just doing colour imaging. So if you are into imaging Mars, and it's a good time to do that now with Mars being fairly high up and coming to opposition. If you've got the right filters, then use filters to image it, and you can accentuate these cloud features, particularly with blue filters. We've still got visual observers, and they like putting south at the top, which is why all their images are upside down compared to the electronic images. But this is a drawing of Mars done by Paul Abel. And he also did this really nice drawing of Jupiter, which shows there the great red spot. So this is the south equatorial belt, the north equatorial belt, and there's the great red spot. And the south equatorial belt has actually been of great interest to Jupiter observers recently, because there's been an outbreak of a bright spot in the south equatorial belt, and you can see it here, particularly in this picture on the left. So this was the day it was identified, which was November the 11th, and it grew rapidly. And it's basically an object of great interest to Jupiter observers. And in terms of imaging with filters, you can image using filters that accentuate the light from methane. And what that does is show objects higher up in the atmosphere. So you can see here that spot very, very prominent in methane light, showing that it's actually high up in Jupiter's atmosphere. Something you can actually see if you look at Jupiter in a reasonable sized telescope at the right time of night. Look out for this outbreak in the SEB. It's not just an imaging target, it can be seen visually as well. And Damien Peach, of course, still observing and imaging Jupiter and getting some of the best results that there are around. And this is his image taken on November the 16th, showing that bright outbreak in the SEB. So this is with north at the top. Jupiter's at opposition today. What that means is that if we see any of Jupiter's moons going in front of the planet, the shadow that they cast is actually almost right behind the moon, because the sun is essentially behind us when we're looking at Jupiter. And there's an interesting event tomorrow, which is a transit of Ganymede, largest satellite of Jupiter, between, what time is it between? Between 22:35 and 00:48 tomorrow night. So if Storm Dara has passed through and there's a miraculous chunk of clear sky, go out and have a look at Jupiter between those times, and you'll see Ganymede transiting Jupiter, and you'll see its shadow right behind it. So that's definitely something to look for tomorrow night if we get any clear skies. I mentioned that Saturn is disappearing into the western twilight. It's disappearing towards conjunction. Saturn at the moment is not what we all expect Saturn to be. So if you look at Saturn in a telescope, you expect to see it with its really majestic ring system. But we're actually coming up to the point where the Earth passes through the plane of Saturn's rings. And that happens twice every 29 years, which is Saturn's orbital period. And it's actually going to happen. We actually go through the plane of Saturn's rings next March, but Saturn is in conjunction with the Sun then, so we're not going to see it. So this is the best opportunity to see, prior to the ring crossing, Saturn with its rings very, very closed up. As Saturn comes out of conjunction next year, once we've passed through the ring plane, there's a period when actually we're on the other side of the ring plane to the Sun. So what we're actually seeing, and it's a very rare thing, is we're actually seeing the unilluminated side of the rings. And that goes on until the Sun passes through the ring plane, which will be in May next year. So when Saturn's a morning object coming out of conjunction, it'll be a difficult object to observe, but essentially we'll have the opportunity to see it with very narrow rings, but also unilluminated. So the rings will essentially disappear for a while, except in very large telescopes. But one of the advantages of having the rings edge on is that the satellites, which move in the same plane as the rings, have occultation and transit phenomena, just like Jupiter's satellites do. And Titan, Saturn's largest satellite, has recently had one of those. This is an example. So this is an observation by Richard McKim of a transit of essentially Titan's shadow across the disk of Saturn. So these events are rare, unlike Jupiter, where we effectively are always seeing the satellites pretty much in the orbital plane of the Earth. For Saturn, we only see these around about the time when we're passing through the ring plane. So they're quite rare, quite difficult to see in this case because Saturn is low down. There is another example of this coming up shortly. So this is the same event that Richard drew from Northamptonshire. This is actually by Mark Radici, who happens to have got a really good gig at the moment. He's working down in Namibia as the guest astronomer at one of these dark sky sites down in Namibia. So he managed to get some images of this, and you can see Titan's shadow here crossing over the disk. Yeah, the next opportunity to do that, to see it, is on December the 22nd. There is again a shadow transit of Titan, this time between 1734 and 2150 in the evening. Saturn will be low down in the west, but if it is clear, the shadow of Titan on the disk should be fairly obvious, and it's definitely something to observe because these things are quite rare. Just a couple more planets then, as we move further out. This is a really nice image. It's again posted on the BAA Observers page by Peter Tickner of Uranus and its moons. So you've got Ariel, Titania, Oberon, and Umbriel here. It's a sort of composite image, but it's a single image processed in different ways to actually not overexpose the planet and then bring out the moons. Oops. On the left here is some more images of Uranus taken by Luigi Moroni in Italy, showing some features on the surface. And then I thought I had to show this. This is an image by James Wakeman using one of these ubiquitous C-star S50s that everybody seems to be getting these days, showing Neptune and its moon Triton. So that's pretty impressive, a 50mm refractor, completely automated telescope that you just plonk down and off it goes and makes observations for you, whilst you go and do something else, I guess. So yeah, really, I'm quite impressed by these things. I was quite sniffy about smart telescopes when they first came out, but they do seem to be very capable things, and their costs now are much more reasonable than they were when they originally arrived. Just then, as the dawn's coming, later in the year, so around Christmas, we've got an opportunity to see Mercury very low in the dawn sky. But it's not a particularly good elongation for us. This, again, is a better southern hemisphere elongation than it would be in the north. So really, it's Mars and Jupiter over the next few months to observe in the night sky, and lots of interesting stuff to see on both of those planets. So move on to rather smaller objects. One of the things that amateur observers do really well is because they're spread out around the world, they can observe a lot more things than professionals can. And in particular, that comes down to occultations. So we had Alex Pratt here earlier on. I'm not sure if he's still here. I think he may have had to go because I think his trains were in trouble back to Leeds. But he does asteroid occultations. So these days, we've got really good knowledge of where stars are. We can predict precisely when asteroids are likely to occult stars. And so people set up telescopes, and this is an example here of an occultation of a star by a faint asteroid. And what you can see here, so look at that star. It disappears and then comes back. And we can use that, if we have multiple observers observing the same object, we can use it to determine the shape and size of an asteroid. And it's a very precise way of doing that. So it's really important work, and Tim Hames coordinates that in the UK for various observers. This is another really good example of that. Peter Tickner, two occultations in consecutive nights, I think it was, or something like that. One of Momenta and the other one of Agamemnon. And again, you can see here the sort of brief breaks in the light where the asteroid is going in front of a distant star. So a key thing for observers who do this is very precise timing. And so you can now get cameras that have built-in GPS that superimpose timestamps on images. but a really impressive work that produces a lot of very important scientific data and which amateurs excel at because there are many amateurs around who can set up on the tracks of where these asteroids are. So asteroids, it was mentioned about the giraffe, that using giraffes as a size estimator for asteroids may lead people to underestimate the danger of being hit by an asteroid. I'm not sure why that might be. But we've now just had the 11th example of an asteroid that was discovered in space that has actually hit the Earth. Now, all of these things are small. They're all of the order of a meter or a few meters in diameter, so they burn up harmlessly in the atmosphere. But it does show how impressive our surveys are now, that we're actually picking up objects in space that are less than a meter in diameter 10, 12 hours before they hit the Earth. So this is the latest example of them. It was put up on the NEOCP, Near Earth Asteroid Confirmation page, as C0WEPC5. It got the designation 2024 XA1, but it only really existed from discovery to being destroyed in our atmosphere for basically something like 10 hours, just over 10 hours. It was discovered at Kitt Peak, and it actually impacted over here in Siberia. Siberia seems to be a magnet for impacting asteroids. I mean, it's a big area, and you know, luckily not many people there. But this is not far from Chelyabinsk, not far in Siberian terms. And of course, Tunguska was up there as well. So if you want to see an impacting asteroid, then move to Siberia, I think. Again, really impressive. So in the period between it being discovered and it impacting the Earth, lots of people managed to get images of it in astrometry. And this is from Mohammed Ode in Abu Dhabi, who got this image, and you can see it here on the time lapse. This was less than an hour before it hit the Earth, and in fact only a few minutes before it went into the Earth's shadow. So pretty amazing stuff. So that's the 11th example. I managed to find this rather cruddy picture of it, but this is it actually entering the atmosphere. So the various websites that do these predictions so far have all been kind of small meter-sized asteroids. I'm waiting to see what happens when we get a 100-meter-sized one, as to how they handle that. We will at least have a bit more than a day's warning for 100 meters, but move to the other side of the Earth, I think, is the idea there. Right, variable stars. I'm not going to mention T Corona Borealis because it's annoying. And Jeremy Shears is going to talk about it next month, and he's going to explain to us why we've all been looking at it and nothing has happened. It will go off at some time, I think. But if you want a variable star that's actually doing something that you can look at, then Chi Sig is here. This is in Cygnus, so reasonably well set up for us. It's a variable star with a very big amplitude, so it's a good binocular variable star. And it has a period of just over a year, 408 days. So Jeremy's saying it's currently going down to minimum, but up through next summer, it'll be coming up to maximum again. And it makes a distinct change to the way that Cygnus looks in the sky when it's at its maximum. We also have this, a really old nova. This is a nova which was discovered in 1901, Nova Persei in 1901. It's got the designation GK Persei. It has periodic outbursts, and it's every 3 years or so it outbursts. The last one was in December 2022. So you might think that the next outburst might be happening soon. So it's an interesting object to keep an eye on that. We also have, in addition to variable stars, we have variable nebulae. And this keeps Nick Hewitt busy as the deep sky coordinator of variable nebulae. Since he's been deep sky coordinator, they've all disappeared. This one, Gael Badagian's nebula, is in Cepheus. The variable star that's illuminating it, this star here, is called PV Cephei. And this is just an example of how much it varies. It varies by a lot, as you can see. It's currently in a state where it's pretty much disappeared, but Richard Sargent got this very deep image. So here's PV Set, here's the nebula, that shows that maybe it's coming back. So maybe we won't sack our variable nebula coordinator yet if you can get it back again. This time of the year is a good time of the year to look at these variable nebulae. The most famous, of course, is Hubble's variable nebula in Monocerotis, which has the variable star R Monocerotis at the base here. There are subtle changes in this, but this one doesn't actually change by very much. And then, who says that the deep sky is not a place you can make discoveries? This is a variable nebula, or at least the picture is of a nothing, but the picture is of where a variable nebula discovered by J. McNeill in 2004 is. This is near M70, is it M78? M78 in Orion. So an area that's worth surveying just in case this variable nebula comes back. And then there's another thing that there's a project on at the moment. There's a recurrent nova in the Andromeda Galaxy M31 called N2008-12A, which goes off every year or so, and there's a big project by professionals to try and get spectroscopy of this nova right after it's gone into eruption. So they called on amateurs to monitor the field. It's in the northeastern part of M31, so the centre of the galaxy is way off down the bottom here, in where that blue circle is. And I'm monitoring it every time I get the opportunity, although that's not very often at the moment. But it should have gone off, well, it should go off soonish. It should have gone off probably by now, but it hasn't yet. So we're all waiting for that. So that's variable stuff. As you can imagine, I might want to mention something about comets. So I will bore you with some comets for the next 10 minutes or so before we finish. So this is the comet that we had back in October 2023 A3 Shushinshan Atlas. And this is a news item from almost the beginning of last year about bright new comet discovered zooming towards the sun could outshine the stars next year. Well, it could do. And in fact, it turned out that it was actually a really good comet if you happen to be in the right place at the right time and have the right weather. There was a lot of rubbish in the media about it. Particularly, they parroted this thing about the fact that it was a comet that had been here 80,000 years ago and you're not going to see it for another 80,000 years. That was a very early estimation of the orbital period. In fact, this comet is a new comet fallen from the Oort cloud, probably maybe a million years from the Oort cloud to us, and it's now actually leaving the solar system. So as it's gone through the solar system, it's been perturbed so that it leaves the solar system. But this 80,000 years thing was everywhere all over the media, and is still all over the media, even though it is completely wrong. So here's another chance, 80,000 years from Galway. But it was a beautiful comet. I was lucky enough to be on La Palma, and we had pretty rubbish weather, but on the one day when it was really needed to be clear, which was the day when we crossed through the comet's orbital plane, it was clear. And so here's the comet with its beautiful dust tail. It's about 20 degrees with a bright forward spike, like a kind of narwhal tusk. So this is very evocative of a comet that was seen in 1957 called Comet Arend-Roland. It's all to do with the fact that we're going through the comet's orbital plane and that we see the dust that the comet's left in its orbit aligned along the orbit plane. So this is an image I took on the night of that crossing the orbital plane. And it's been an ambition throughout my life, being a comet observer, to see something that looked like Arend-Roland, and finally I have done. So I'm really pleased about that. I was on La Palma with Nigel Evans, who's somewhere in here. There he is. So this is pretty impressive. This is a GoPro, right? These are the cameras that you make stick on your helmets when you're cycling down hills or skiing or whatever. But they're really good for astronomy as well. And you can see in this wide-angle image, there's the comet going down, and you can even see its anti-tail as well. And this is in a tiny little GoPro camera. So Nigel took lots and lots of pictures and have strung them together into lots of interesting time lapses. So we were observing this comet from about 2,000 meters up on the mountain in La Palma. So we actually saw it setting into the clouds below us. So really impressive sight. So very typical of comets. It was very impressive if you happened to be in the right place at the right time and you had clear skies. If you were not in the right place, or you had light pollution, or if the cloud was poor, you might say, nah, what was all the fuss about? There was really no comet. But I can assure you it was a very impressive comet if you were in the right place at the right time. And then just finally, this was on the next day, but just showed you the amount of cloud that we had to deal with. We were at 2,100 meters near the observatory, where you'd expect it to be clear all the time. But in fact, for a lot of the time we were there were clouds that we had to battle with. It's faded a lot now. It's heading out of the inner solar system. This is an image that Alan Rains sent me. He happens to be on Tenerife at the moment, so this was from Teide National Park, taken, I think, a couple of nights ago, showing the comet here, much diminished in size, but starting to cross over the very dense star clouds in Aquila. So we've definitely seen the best of that comet, but it was a very impressive comet, and it was incredibly well behaved. It followed its light curve very well. It was most unusual for a comet. It did what was predicted of it. Here's something which is a comet which we have under observation a lot. This is the comet 29P, Shashman-Bachmann, which is an unusual comet. It's a large nucleus. It's in an orbit sort of out at Jupiter, so it's not in the normal kind of elongated orbit of a comet, and it suffers major outbursts frequently. And there's a BAA program to observe this comet that's run by Richard Miles, who got the award earlier on, to effectively look at this comet and see how it outbursts. And it's a really good example where amateur observations have managed to accumulate a huge amount of information about the behaviour of this comet, which appears to be contrary to what the professional theories say this comet should be doing. But the professionals are ignoring that, or at least they're very reluctant to sort of embrace what we've observed. But it's clear that this comet, when it goes into outburst, it goes into outburst very quickly. It has a very quick release of material, which then stops. And so you see this very characteristic light curve, where you get a sudden rise and then a gradual tail off. Certainly something, it's ideally placed to observe. It's a really interesting object, and if you want to do sort of comet imaging that's going to be really useful scientifically, it's a really interesting object to observe. Here's an image of it shortly after the last outburst, where you get this kind of inner coma, which is the material that's come off the nucleus, superimposed on a fainter outer coma, which is from a previous outburst. And we've got here a nice sort of time lapse of that. And then just one more comet before I move on to the final bit about meteors. Comets are a bit like buses. You know, you have none for a long time, and then you have a few interesting ones that come along at short notice. We had Shuxinshan Atlas. We've now got this comet, 2024 G3 Atlas, again, discovered by the Atlas survey. It's a sun-grazing comet that will come to perihelion on January the 13th? I think, January the 13th next year, at a distance of only 0.09 astronomical units, so very close to the sun. So that tells you that it could potentially get very bright, but that it will be very close to the sun when it does get bright. At the moment, it's visible from the southern hemisphere in the morning twilight, very, very low down, but making some magnitude estimates, John Shanklin has generated this light curve, which goes up to the dizzying heights, potentially, of kind of -8, -10. But at the time the comet is this magnitude, even if it does achieve that magnitude, it's only 4 degrees, 5 degrees from the sun. But there is a possibility of seeing this comet just before perihelion, even from here, if it's particularly bright in the morning sky. And then after perihelion, the comet could have quite an interesting tail in mid to late January, but it's definitely favoured from the southern hemisphere. I did stick in one final comet thing, which I thought was quite interesting. So Roy Panther, who was, I think, the last discoverer of a comet, was Alcott the last visual discovery, yeah. Yes, that's true, because Jonathan's discovered lots in Soho and
not lots, a
few. Anyway, so Roy Panther discovered a comet. He discovered it on the night of 25th of December, 1980. And recently, Richard McKim has been able to go through his notebooks and found this very interesting note in his notebook. So here we have, you know, he's just discovered a comet, 1980, December 25th, blah, blah, observing whatever. Only M56, apart from discovery of a new comet. That's all he says is in his notebook. So that's Panther's discovery of his comet on Christmas 1980. We've got the Geminid meteor shower coming up. So basically this is showing you the activity of meteor showers. We have the Geminids coming up on the 14th, 15th of December. Then we have the Quadrantids coming up on the 3rd of January. Unfortunately, the moon has really messed around with meteor showers this year. It's going to be full moon on the night of the Geminids, and it was in the Leonids. So these are some images by Callum of some Leonid meteors. A nice bright one. This is the moon. Clouds lit up by the moon. So the Geminids are going to have to fight with that very high up, very bright full moon on the 15th of December. But still worth going out and just having a look because it's quite an active shower. The Quadrantids are a little bit better off. They're on January the 3rd, first quarter's on January the 6th, so the moon's quite a thin crescent. So lots to look at and observe, and I can see Mike's looking at his watch because he wants to get to the wine. So I'm almost finished. I just want you to indulge me by looking at this last video. So I'm really interested in spaceflight as well as astronomy, and the Starship launch. That's upside down, Janice. Right, it's almost done. Starship launch, the 5th Starship launch had this amazing thing where they recovered the first stage. And there's an amazing website that's got extraordinary video on it, and I just go and have a look at it. It's called Everyday Astronaut, where people have gone out with telescopes and cameras to video things. This is the returning first stage from the Starship launch, coming in supersonically, so you can't hear anything at the moment, coming in to actually land at the point it got launched from. So this is just incredible stuff, and whatever else you think of Elon Musk and whatever, SpaceX has done some amazing things. So look at this. This stage is coming in to land. It's going to land at the actual launch gantry where it took off from. And get grabbed by the Mechazilla thing. So the more recent Starship launch, they actually didn't do that. They deposited the first stage into the ocean. But it's pretty amazing stuff. And I think we probably will have people going to planets sooner than any of us really think, the way things are going at the moment. So that's a thought to go with for Christmas. So happy Christmas, everybody. Enjoy the wine. Sorry to have kept you for longer than a minute, as Janice said. We finished now. So happy Christmas, everyone. The wine is outside.
Oh, thank you, Nick. I'm a bit worried about noting that an asteroid's going to hit me and knowing for a year or something. I don't want to know at all, you know.
Well,
it's going to hit the Earth.
Spend that year doing the things you've always wanted to do.
If only. Okay. Right, well, I'm not obviously going to keep you far from the wine because I think I'd probably get run over, mobbed, whatever. I have a couple of things just to say at the very end. First of all, just check under your seats and your chairs you haven't left cups or glasses or anything. As you know, we have the use of this room. It's a great favour from the Institute of Physics, so let's respect their kind hospitality. I want to say thank you. I've already said thank you to Simon for all his hard work. And I also want to say thank you to Hazel Collett, who has been organising the Institute of Physics meetings, the London meetings, for, how many years?
Many.
Bless her. Like the typical herding kittens. So everything went fine. Our speakers all managed to get here. Thank you to our wonderful speakers. You'll be able to ask them further questions as they've kindly stayed to join us in a glass of wine, but no longer than 3 minutes each. Everybody's going to have a chat. And they want to relax as well. I want to wish you all a very Merry Christmas and a Happy New Year. It's great to see people all starting to come back in person to our BAA meetings. And thank you all for coming. Have a nice time. Enjoy your wine, juice, whatever is your tipple. Thank you. Good night. So cool.